let me thank everybody who's here for coming to this session on basic and fundamental problems in quantum information theory. And the first talk is going to be given by Jaroslaw Brukner from the University of Vienna. Caslav has done very interesting work in a lot of subjects. I guess lately Wigner's friend, and also what he's going to be talking to us today about, which is indefinite causal order. So let me go ahead and turn things over to Jaroslaw, and then we will proceed with the talk.
So thank you, Mark, for the introduction. It's a great pleasure to be, well, not at your place, but to give a talk at least on distance. I'm going to talk about indefinite causal order, as already Mark said, and I was asked to give an overview talk. So, and not to leave out the main two aspects of quantum causality, namely usage of this resource for quantum information processing on one hand, and the notion of causality in gravity on the other hand. And so it will be a little bit of everything, but I hope that if you are not really active researcher in the field, you will find it useful. So let me start sharing my screen. Okay, I hope you see the screen. So as I said, it will be from the fundamentals to really a more applicative side of this research. So here's the outline of the talk. I will first introduce what I mean with quantum causal structures. And then I will define so-called causally non-separable processes. So these are the most interesting processes which feature indefinite causality. And I will say something about a more concrete example of that, the quantum switch. And then I will move on into applications of quantum causality in the field of quantum information. Finally, I will a little bit speculate about physical realization of genuine causally non-separable processes, for example, via superposition of large masses. So when we think about a quantum circuit, what we mean with this is, in fact, very close to the notion of definite causality, because we think about systems on which we apply certain gates in sequence. So what you see here is a typical quantum circuit with maybe some source, and then we have wires which represent actually quantum systems sitting maybe localized in space, but of course changing across the time. Then each box here is a single use of transformation. And I distinguish here between the red boxes, which could be a fixed structure and not able to move or change. And then there are free slots from M1 to M4, where we can insert some gates by the choice of an agent. And the whole input-output proceeds from bottom to top. And what is also important, there are no loops. That's why we think of that as a definite causal order of the gates. But let me now color one of those gates, and I'll call it presence. And we will see then that the quantum circuits and the structure of quantum circuits is very close to what we understand as space-time causal structure, because we can define a kind of a future light cone. This is the green area. These are all gates that can be influenced by the free choice of our operation at the blue gate. And also we can define a yellow pass light cone, if you want. These are all gates that can influence what is observed. For example, if we have some kind of a measurement or CP map at the blue gate. And why I'm saying this? Because, for example, M4 can be influenced by the choice of the blue one, because we because it's in a direct line connecting the two of them. And a similar M1 is a direct line of that. But of course, here, for example, even something what will be on the left upper red line will be influenced by the choice of the blue one, because we have an entangling gate between the first and the second line. Now, as I said, this is very similar to the causal evolution in space-time, and then at the end, it's not a surprise why quantum causality, investigation of quantum causality is important both in quantum information but also in space-time physics. On the right-hand side, we have the similar situation in which there is a blue point, presence, where we have a light yellow pass cone and the green future light cone. And we have gates that we can influence, like M4, we can influence by the choice of the operation at the blue one, but M3 we cannot influence. It's a space-like separated, just like on the left-hand side. Now, what the quantum causality aims for is weakening the notion of causality. And the idea is that in typical situations that we should face in a quantum gravity framework is that the causal order or metric is not well defined. Why? Because there are some fluctuations of the metric, either on a Planck scale, or because maybe the source of gravity is a quantum source put in a superposition at two positions, for example. And exactly this situation was addressed by Butterfield and Isham in this paper, where they point on the difficulty to even imagine what in this situation can happen. And they write, once we embark on constructing a quantum theory of gravity, we expect some sort of quantum fluctuations in the metric, and so also in the causal structure. But in that case, how are we to formulate the quantum theory with the fluctuating causal structure? And indeed, this seems very challenging, because all our theories pre-assume a definite causal structure. That's how we that is how we, for example, construct the gates. We know which gate can influence other gates, and so on. This question was also posed by Lucien Hardy some time ago, and he developed his own framework, causaloid framework, for probabilistic theories with non-fixed causal structures, starting from 2005. And it is a very influential work that inspired us also to develop our own framework to deal with these situations, which is a process metrics framework, and I will tell about that in short. Now, still, let us build up some kind of intuition about the situations we want to deal with. Imagine that we have events, but events are not the points in a manifold. They will be defined operationally, like a pointer of a clock at B, or maybe some explosion at A. And imagine that they are specified purely by kind of observations or measurements, in a way operationally. Now, if I abstract these 2 points, and that they are spatial temporal distance, will be governed by the metric they are imposed on a manifold. So maybe in some metric G0, I will have a situation in which the explosion will influence the pointer on a clock at B, but maybe with some other choice of a metric, they will be causally independent from each other. Now imagine that somehow I'm able to prepare a superposition of these 2 situations. And then we see that as a consequence of that, A, B could be in a superposition of either being causally independently or causally dependently, such that A is happening before B. I put, of course, these cats under inverted commas because we don't have developed any formalism, and we don't have a Hilbert space on which we can define these cats, but just as a kind of a illustration of what we are aiming for. And interestingly, maybe at this point, it's good to remind us that people have thought about that already in the 50s, and there is a beautiful proceedings of a Chapel Hill conference and the discussion among several physicists, among them also Feynman. Now, let's move to the quantum causal structures. First, I remind you on the notion of a quantum transformations. Abstractly, the most general quantum transformations, or instruments sometimes called in quantum mechanics, quantum information theory, are represented by complete positive map. And so what we have here is a picture of an instrument. We have an initial state from some input Hilbert space on the space of linear operators over some Hilbert space H1. Then we have two classical data, namely the setting, which agent can choose which complete positive map to perform. And then there is some outcome coming out of this device, which we defined as A. And finally, there is also a system coming out. For example, if you perform some unitary or weak measurement, in general, we do not destroy the system, and we have an output system which lives in some LH2 space. So this will be the element which we can associate with every possible laboratory. Now, we know how we define a definite causal order in ordinary quantum mechanical framework. And here is an example of this. Imagine that now Alice and Bob have access to certain instruments that are represented by complete positive maps. And here I also introduce POVMs as a subset of that. And there is also a quantum channel between them. Now we can imagine that there is a source sending a state towards the Alice laboratory. Alice performs some operation and subsequently sent out the system towards Bob, who at the end can perform, for example, a measurement. Now, probability for this situation, which I call A before B, is given with this kind of Born rule, in which the causality is embedded in the formalism itself, because the sequence of these operations is represented as a composition of the maps, such that the first map we perform on quantum system is Alice map, then there is some channel, and finally Bob's. Another very typical situation, which still is in line of a definite causal order, is a sharing, in general, entangled state between two systems. And I will call also definite causal order because in that case, as compared to the previous and contrast to the previous case, Alice and Bob cannot send signal to each other. So it's a kind of causally neutral situation, and I will add this situation as a part of a definite causal order framework. Here we have a state, and it's shared and sent to two maybe distant parties, and the two parties apply their corresponding maps. And again, now in that case, when A is causally independent from B, probability is given in that form, where the maps are composed in a tensor product and then applied on a shared state. Now, first, I would like to turn your attention actually on the fact that in the two cases, and I go back, when we have time-like separated experiments as compared with the space-like separated experiments, the two expressions differ from each other. In one case, we use the composition of the maps. In the other case, we have a tensor product. So they're not really very symmetric, although we like to say that in a general relativity, we speak about space-time. So here we really need to know in advance what is the causal relation between the maps, such that we, apply a proper computational tool to compute the probabilities for correlations. And of course, I didn't mention, but you realize that this PAB given XY are probability to obtain the result A and B on Alice and Bob side, given that the setting chosen on the two sides are X and Y. Now, I'm slowly now building up a necessary kind of formalism, and this is the minimal one, I will not drill into that, is how to describe situations that go beyond the two cases of a definite causal order. And for that, I need the Choya-Mikulski isomorphism. And that's an isomorphism that allows us to represent a complete positive maps with positive matrices or two-state density operators. Namely, we can represent the complete positive map with a matrix that I write as a capital M A given X, result A given X setting, in a way that we first start with a maximal entangled state, a non-normalized maximal entangled state phi plus, which is the sum II, and then we apply only a part of this system to this map. And this state that we obtain in that way is the Choya-Mikulski representation of the map. And from now on, whenever I talk about map or some instrument, what I will mean mathematically, that it is represented by this positive map. Now, I'm coming to the first slide to introduce you the process matrix formalism. Imagine that you have some region of space-time, and this region of space-time will be described with some yet undefined causal relations between different parts of this space-time. And I call this element in our framework W, or this will be the process. Now, in this space-time, I can embed some laboratory. And what I mean with this more concretely is exactly a quantum instrument. This will be a map that will have an initial Hilbert space where some system will enter this instrument or this laboratory. And this is the Hilbert space A1. Then I will apply some local map on this system and send away the system out of the laboratory. But I will not only have one laboratory or one patch of space-time, which I, in this case, identify with each other, but I can have many of them. And so this is an analog of the quantum circuit picture from the first slide, but with an important difference that I don't connect in advance the outputs of one laboratory with the inputs of the other laboratory. If I would connect them, that would mean that they are causally related. That, for example, if I connect output of A with the input of C, then this would already mean that A is before C. I leave it open. I say that I don't know anything in advance, and maybe it's not even defined what the causal relations between them. All what I know are which operations have been performed in these A, B, C, D, and E laboratories. And there is something which connects outputs of laboratories with the inputs of some other laboratories. And this what connects them is W. And now I want of this very kind of general framework to give me a meaningful probabilities. So at the end of the day, I would like to have something as probability for correlations, given that observers choose certain settings, what is the probability they get certain outcomes? And so I write here on the left-hand side, probability for this joint event, MAX and BY, and so on. And furthermore, I want this to be as close as quantum mechanics, the standard formulation of this. And so I have a kind of a generalized bond rule in which I have this representation of the maps given through the tensor product and the W which connects these laboratories. Now it turns out that if I want to have so general this framework, and yet I want to have probabilities which are positive and normalized, there is some restriction on W. It could not be any possible positive matrix in this huge Hilbert space, but it has to satisfy certain conditions that I will not go into right now, because this will move us away from the main task for today to see the relevance of this research. But one can, out of the conditions of positivity and normalization, see that W should satisfy certain conditions. We call these physical conditions for the process matrices. And this comes alone from the very natural assumption of positivity on normalization. Now, here are examples of the W matrix in the cases of a definite causal order that we have introduced in the standard formulation. And I will want to convince you that the formula that I gave as a generalized bond rule actually works. And imagine here that we have a source that is again shared by two parties. And this source sends the particles such that one particle enters the input Hilbert space of Alice lab A1 and the other one a B1 of Bob. Then the W that I can assign to this situation looks like that. We see that the state enters A1 and B1, and then we have a trivial identity, trivial outputs, because we don't send the system after the laboratory. And it turns out that this probability that I have introduced before in the standard formulation can be recovered by our generalized bond rule if I insert this W, and of course I have corresponding but arbitrary CP maps of Alice and Bob. The same formalism also works in the case of a definite causal order. The situation is slightly different. We have a state, again, that is sent to Alice. Alice receives this to A1, send it out from Hilbert space A2, again to the input Hilbert space B1 of Bob. And this is represented very nicely in the W, which I call now A, like precedes B, because the row is given in the input Hilbert space of Alice. Then I have a channel that connects output of Alice and input of Bob. And again, the same formula works here as well. So the first things that maybe it's important to note here, that this W formalism or process matrix formalism allows you on equal footing to treat the two situations that are causally different, namely the same generalized bond rule is applied in both cases, and we don't need to care about having different trace rules or different ways of putting the maps one after the other, either composition or tensor product, depending on the causal structure. The causal structure is here encoded in the W itself, but the formula is always the same. This is a nice, maybe even practically useful property, but it still is not why we should use this formalism. The reason we want to use this formalism is because it actually is richer than the standard formulation of quantum theory in a sense, and allows indefinite causal structures. And we will come to this very shortly. Now, here I just want to kind of, for completeness, say that we can, of course, reverse the order of Alice and Bob. We can have a Bob before Alice, sending state through to the input of Bob, and then output to Bob through the channel to the input of Alice. And then basically we have the same situation. It's just that Bob precedes Alice, but the Hilbert spaces that are denoted here in the W takes care about the causal order of these operations, and the formula is again the same. Now, the question that we have posed back then, and this is already some time ago, is that we can, of course, think of something which is not very surprising, namely that we have a classical mixture of definite causal orders. We can toss a coin and then decide to send the system either first to Alice and Alice then to Bob, or the other way around. And then we will have something which we'll call causally separable processes. These are those processes that can be obtained by the convex mixture of processes where A is before B and B is before A. And this is, of course, something which is also not surprising, can be understood either as an ignorance of an observer about which order operations have been performed, or maybe in active interpretation, really on the basis of a classical control bias can choose one or the other to perform one or the other process. Now, what is the most interesting question is, are there processes for which this is not the case? Are there physically allowed, in a sense, from formalism, allowed processes that give rise to positive normalist probabilities that cannot be understood as a classical mixture or convex mixture between well-defined causally ordered processes? And the answer was provided, interestingly, even before our paper, and this was given in a nice paper by Giulio Chiribella and co-authors back in 2009, when they introduced a process for which they have 3 parties, not 2, and for which this is really the case. Of course, they were thinking about in a framework of quantum computation, but now when you look at the example that they provided, this is a process for which there is no definite causal order. It involves 3 parties, and it's known under the name the quantum switch, where you have to distinguish between the control qubit, which is either 0 or 1, and the psi state of the target qubit. And what you have here is that depending on the value of the controlled, the order of operation of Alice and Bob will be different, such that, for example, if I have the control at 0, then first Alice acts, then Bob, and then Bob sends it away to some measurement device of Charlie, who will measure the qubit, who will measure the control always in a 0 plus minus 1 basis. The other possibility is that the control is in 1, and if this is the case, then the order of 2 operations is inverted, and Bob acts first, and after, then Alice. Here in this picture, we consider a very specific representation of the quantum switch, where, for example, in a quantum interferometric setup, the control could be the path of the particle in the interferometer, whereas the target could be some internal degrees of freedom of a photon, for example, polarization. And when one thinks about quantum interferometry, then maybe one also understands why one needs the measurement at the end. Because if I would measure if I would not have a Charlie's measurement, I could measure the path of the photon, and therefore I could, by knowing which path information, also know who acts the first, and therefore that will be not a genuine quantum superposition of different causal orders. However, the Charlie measurement is in interferometry just the second beam splitter. After this second beam splitter, we delete any information about the path and therefore about the order of action. Now, the proof that this is indeed a process which cannot be described as a classical mixture of definite processes was given in these 2 papers. And very recently, I want to turn your attention on a very nice and exhaustive research about all type of processes in which we use coherent control of systems. And this is in this work, recent work by Branciard et al. Now, for completeness, I also want to briefly tell you that there are also processes which are indefinite features, indefinite causal order, but are not of to be understood as a quantum superposition of different causal orders, as is the case the switch or coherent control of circuits. And that's a nice series of papers came out of Lugano from Emin Baumeler, Stefan Wolf and also co-authors. This is something more recent, in which there are processes that do not involve even quantum superposition. So in a sense, all W's are diagonal here. We can call it classical processes. But however, there is no definite causal order. And my view of understanding that this arises not because of quantum superposition, what was the case in the switch, but rather because of topology, if you want, because they present certain causal loops. And this particular process is a three-party process, which is, again, causally inseparable, where we have two possible loops. And whether we have a loop which goes clockwise or counterclockwise for the three parties depends on the output coming out of these laboratories. So again, in every laboratory, we receive the system, we perform some operation and send out. And now if the majority of the outputs of the three outputs is 0, it goes clockwise. And if the majority of the outputs is 1, it goes counterclockwise. And it could be shown that this is first a process with indefinite causal order. It features some kind of causal loops, but very innocent causal loops. And this is really inherent in every process matrix formalism, that these processes do not feature ground feather paradox. I can talk about maybe in the question time more about that. In any case, you can perform any arbitrary operation within the laboratory, each of them, and they will not be able to give rise to the grandfather paradox, or in other words, to send signal to oneself in the past. And also what I will not have time to talk about is that these processes violate a notion of causality in the strongest possible way. They violate so-called causal inequalities, which is device-independent way to prove indefinite causality in a similar spirit as Bell inequalities are device-independent proof of non-locality. Now, I would like to move to quantum information processing on indefinite causal structures, and to show you that they are useful resources. And first, I would like to introduce Kiribella's example of a promise problem, which is the following. Assume that you are given two boxes, and all what you know that in one box is one unitary and the other box is the other unitary. And you need to decide whether these two unitary commute or anti-commute. And you are given the promise that one of them is realized. Now, it turns out that the switch is very useful for this to solve. And this is maybe most easily seen really in the terms of quantum interferometry. If you think about the beam splitters at the beginning, and then two possible paths, the black path in which you first go through U0 and then U1, and the gray one, which you first go through U1 and then U0, and then you overlap the two beams on another beam splitter. Now, in terms of a quantum circuit, what we apply first, we have a Hadamard on the control, which is the path in the interferometry. And then we apply what we like to call the two switch. And the two switch is something which conditionally on the value of the control give a certain order of unitaries. So if the control is 0, then the order of U0, U1. If it is 1, is the opposite. And finally, we have the final Hadamard. And when you do the final Hadamard, the output behind the beam splitter, it looks like that. You see that depending whether you will see 0 or 1 result after the Hadamard, you will get one or the other outcome depending on whether the two commute or anti-commute. But you have a promise that one of them will be realized. So you get with certainty one or the other result. In other words, if you measure behind the second Hadamard in the basis 0, 1, you will find out whether they commute or anti-commute. Now, what is interesting is that in this case, you query each of the boxes only once. And now, here is maybe a conceptual issue. What does it mean, querying or asking the box? Usually, when we have a quantum circuit, we just count how many gates, how many times a certain gate appear in the quantum circuit, and that gives us the number of queries. But here we have a strange situation, because this is not in general, in the narrow sense, a quantum circuit. It is a superposition of two quantum circuits. The lines that I draw here are not the lines along which the quantum qubit is localized. It's rather something which denotes a subspace. It's really or a path in the interferometer. So it's not obvious how many queries we have in this setup. And one way to circumvent this was proposed in our group in 2015, where we attached in each box a counter. And whenever the photon enters the box, the counter goes from 0 to 1. And when you put this counter in the two boxes in this setup, the counter will show 1 in each boxes and will factorize out from the circuit such that you will be able to complete the task and yet know how many times you query the box. So it will not destroy the circuit. Now, if you want to do the same, but without the quantum switch, without the quantum indefinite causal order, you will need to query at least one of the boxes twice. Here I put a picture where I have 4 times, or although it's enough 3 times, but this is a picture that then easily scales. The situation is that depending on the value of the control, I perform the swap gate. For example, if I have a control 0 and 1 value, then I will swap for the z value psi with A0, go to U0, swap back. Then I here have a 1. Then I swap maybe to U1 and go back. So it will be U0, U1, and I will have a definite causal order. But if I have a indefinite causal order, then the control could be in state which is 0, 1 plus 1, 0, which will give rise then to the superposition of two causal orders, in which I have the unitary U1, U0, U1 plus U1, U0. But nevertheless, if we look at how many queries we perform in this circuit, we have 4 of them, because we just count how many times the gates appear in the circuit. Of course, as I said, one can do it with 3 queries, but if you go and scale the system, this is the picture that will be easily scalable. I should say that since then there will be many experimental demonstrations, including the Andrew White and Queensland group, John Wei Pan group, and many other groups. The first experiments have been performed in Vienna, and where indeed the quantum switch was implemented with the control being the path degree of freedom and the polarization being the control. And here's basic setup. You create the control here's a beam splitter in a superposition such that one amplitude goes through U2 and then through U1 and then to the beam splitter, and the other goes through and then U1 and then U2 and then goes to the beam splitter. And for the purposes of this task of the promise problem, one can show that the probability of success of guessing after performing this experiment was within the error better than what you can achieve with a causally ordered circuit. Now, one of the questions that we posed is, do we have an advantage in the asymptotic case? Namely, yes, we see that, well, one query each, so 2 queries is less than 3 queries. We have kind of an absolute a constant advantage, but we usually in the quantum information theory want to see how this problem scales. So do we have an advantage in the asymptotic case when we have many boxes? And the problem is slightly more complicated in that case, where you now, instead of 2 unitaries, you have n unitaries. And the problem is, and the situation is like that. There are unitaries which are somehow ordered from u0 to un-1. And then we can perform some permutation of this order, which I denote by px is a permutation. Now, if I permute these unitaries, then the relation between this new order of unitaries with respect to the old one, is given by this omega xy, which is certain phase. It's a phase. And there are n factorial different y's, n factorial different properties. Each property being how this phase arises when I apply a certain permutation of the unitaries. Now, we have again a promise that that they certainly satisfy one out of these n factorial properties, and we need to find out which one they satisfy. The example for n equal 2 is actually exactly boils down then to the problem of commuting and anti-commuting unitaries. Now, again, in all these situations, like in any quantum information result, it's much easier to show the quantum algorithm than to show that the classical cannot achieve what quantum promises or does. And here is the problem how to solve it with the n switch. So the n switch is generalization of the 2 switch, in which we apply the permutation x if the control is in some x value. So it's really like we apply on the target permutation of these unitaries if the control is an x. Now, how the algorithm works. First, we perform the control in superposition, and we have n factorial values for the control. Then we apply the n switch, and of course, now we have a superposition of different value of controls with different order of unitaries. Then we perform the Fourier transform, which is a generalization of the second ring splitter, if you want, or a Hadamard. And then at the end, we measure the control and get the result with certainty of which property they satisfy. Again, y was enumerating the property of the unitaries when we permute them. And so this is the quantum result. It distinguishes between n factorial sets of n unitaries by querying each box only once. This we can prove again by the means that I explained before. So altogether we have n queries. Now, can we do something, and how? What's the complexity of the causal algorithm? Back in 2015, we thought that possibly the best possible algorithm is to simulate the n switch. And causal simulation of the n switch is just the scheme that generalize, as I introduced this before. So now we have here, for example, 3 boxes, and we have 3 controls, and then we have a swap, and we can put the controls in superposition such that in the end we have a superposition of the different orders of unitaries. But we see that this scales now such that we have 9 queries. Each box will be queried 3 times. And this goes on then, basically for n boxes, we will have n squared queries. But still, we can ask ourselves, can we simulate the N switch more efficiently? And this is related to the question from, well, permutation theories, which is the question, what is the length n of the shortest sequence of n characters containing all the permutations as subsequence? Because if we have such a sequence, then we go in causally order through this sequence, and we will have all possible order of unitaries. So we have n characters, we have all possible permutations, and we want to find the minimal length of the sequence of these n characters such that all permutations are there. That would something which will simulate the N switch, because in that way we can have all possible permutations. And this is an open problem in combinatorics, or at least back then it was an open problem. But they are following bounds, which are basically, it scales with n squared. And so one can say, you see the lower and upper bound basically scales at n squared. We can conclude then that if we want to causally simulate the N switch, the reduction of the query complexity goes from n squared to n. And I want at this point also to mention a very nice theoretical and experimental work that came out by Tadei et al. In 2021, when they really adapt this problem to be more experimentally friendly, and you have a very nice switch. So something which really goes in the complexity of experiment, but also in the theoretical results in interesting direction. Now, the question still remains whether the gap is linear, because all what we have proved so far is that the classical simulation of the N switch scales with n squared. But maybe this problem can be solved in a different way with more efficient causal algorithms that will not simulate the N switch, but will be solving the problem. And indeed, that is the recent paper by my PhD student, Martin Renner, which we put on the archive, where we found the causal algorithms that do not simulate the N switch, and that solves the only known specific that kind of Fourier promise problem with n log n queries, and the causal algorithm that solves every such problem with n square root of n. And what we use here, and I will not go into details of that, is that every set of unitaries that satisfy the promise of a Fourier promise problem also satisfies certain pairwise commutation relations. So basically, there is more structure in these problems that were overlooked before, and that help us to reduce the gap between solution, N switch solution and the causal solution. Basically, it's now sublinear. And of course, we also have no proof that is the most optimal classical algorithm, or not classical, I'm using maybe sometimes classical. What I mean with is a causal algorithm, and maybe the gap is even smaller than that. Now, I see the clock a little bit I'm looking at. I want to really finish in time, and I also promised to say something about relevance of this research in the framework of causality in space-time. And so for that reasons, I will just mention the main result without going into details in quantum communication, where if more precisely communication complexity problems, these are the problems in which it turns out that indefinite causal order can provide really significant advantage over the causal algorithms. And maybe one slide about what communication complexity problems are, and then stating the result of us. These are the problems in which partners need to compute some function or have some joint task, but the inputs for this task or the inputs of this function are distributed non-locally. For example, Alice receives X and Bob receives Y, where they have to send the result f, x, and y, or some other partner, maybe Clara, needs to compute the result of the function given these inputs. And obviously, the most trivial thing is that Alice sends x to Bob, and Bob sends x and y to Clara, which computes the function. But the question is always whether this can be done with really little amount of information, and obviously less than what is the size of the whole input. And it turns out that these problems could be relevant whenever, for example, classical communication is expensive, maybe in the deep space, but also when you want to optimize distribution and computer networks. So we want to reduce the number of bits or qubits exchanged between the partners and nevertheless finish the task. And now I will not go into this task, but I will tell you that it turns out that we have an exponential reduction of the communication complexity in the case of when we use the quantum switch as compared with the causal algorithm. And this was also recently shown with an enormous number of dimensions, 2 to the power 13 dimensions. The advantage, basically what you see here is how many bits has to be transferred between the partners as the system increases. And any classical protocol would need a lot of information to change, but even every causal quantum protocol will need something which grows exponentially with the size. However, the protocol that was implemented goes linearly with the size, and this shows an exponential advantage of the setup. Now, for the rest of the time, I really want to go into engineering space-time, if you want, and so-called gravitational quantum switch. And I also excuse myself for those who have seen that, but given that I was asked to give an overview talk, I wanted to get to the most simple example of indefinite causal order in space-time. And so causal order, as at the very beginning of my talk, is given by the, so to say, light cone structure. And if we have some even A, it can either influence the B if it is in a future light cone, or if it is space-like separated, they are causally independent. And of course, B can influence A if it's in its past light cone. Now, I need to remind you on a known effect from special and general relativity. Here, I will go to the gravitational time dilation. And this is the fact that when you have two synchronized clocks, which are placed at different gravitational potential, then those clocks will eventually show different times, because the clock which is closer to the source of gravity ticks slower as compared to the one which is further away from the mass. Now, exactly this gravitational time dilation will be the crucial element to show that by placing the gravitational sources in certain configuration, we can realize the quantum switch. And for this is also important to start with a setup where there are no masses. We have two laboratories, A and B. And basically what this point A and B indicates are really small laboratories, if you want, so small that we can apply our complete positive map or instrument. And let's assume that at the very beginning, Alice and Bob agree to perform certain operation, for example, apply the unitary for the incoming photon at time 10 past 10, as it's here drawn in this picture. Now, if they synchronize clocks and they are space-like separated, these events cannot influence each other. So whatever Alice does and sends away the photon, it will never reach Bob. So there is no communication. It's an uninteresting case. But here is a situation change because in general relativity, causal structure is dynamical. It can be influenced by placing the masses appropriately. And so what you see here is still Alice and Bob want to follow their agreement to apply their operations at 10 past 10 local time. However, I put a mass closer to Alice than to Bob. And this is a very large mass, which will induce a time dilation. And the time dilation is so large, and here is this indicated by very large interval between ticking of the clock as compared to the small intervals of Bob's side. The time dilation is so large that when Bob applies an operation at 10 past 10 and sends away the photon towards Alice, the photon can arrive in time such that Alice can apply according to her time 10 past 10, her operation. And this 10 past 10 is here, of course, abstractly with tau star denoted. And so in that way, we can, by placing the mass closer to Alice, kind of open the channel from Bob to Alice. Bob can send the information to Alice, and this information, or it can send a photon such that the photon enters his lab just and his local time, tau star. He applies operation and sends away, and then we have a sequence of unitaries, UBUA, where the local event in both cases is entering the photon and applying the operation at 10 past 10. Now, maybe you already know what I want to do. I want, of course, to somehow superpose these situations. Here I have two possible configurations of the mass, one on which the time dilation is larger in Bob's side than Alice's side, and the other one the other way around. And because causal structure depends on the mass or stress energy tensor in the causal path of the events, I can influence then who will act the first by placing the mass on either closer to Alice or closer to Bob. Or in a very kind of futuristic experiment, I can think about having a beam splitter for a large mass, which I can either place closer to Alice, or I place it closer to Bob. If I place it closer to Alice, Alice will be time dilated with respect to Bob. Bob can signal or can send the information before Alice, and we will have one sequence of unitaries. If the mass is reflected such that it ends up closer to Bob, it's the other way around. And what we see here is nothing else than by quantum controlling the order of unitaries, and we quantum control the order by a specific configuration of mass. So the control is the position of the mass, and the target is again whatever on photon, maybe a polarization. Okay, with this, I would like to come to the summary of my talk. What I try to argue that global causal order need not be a necessary element of quantum theory, that we can have a coherent and consistent framework to describe also situation when the causal order is not well defined. Then that there exists, I mean, even experimentally, implemented causally non-separable processes like the quantum switch. There are also more very strange, maybe causal processes and non-causal processes like Lugano processes that I mentioned, for which we don't know how to implement in the lab, and which seems to require a certain loops. We have shown that we have less sufficient kind of what was previously assumed computation based on the switch or indefinite causal order, that for the problem, a specific problem that have been investigated, we have a sublinear advantage in computation. What I didn't show in full details, that we nevertheless have an exponential reduction in communication complexity using this resource, and I'm happy to tell you about that in question time. And what I also try to argue, that the quantum switch can be realized by spatial superposition of large masses. This is a whole new research field that we are following and extend also to situation in which we have, for example, quantum clocks that gravitationally interact with each other. And also there we can see that we can produce situation of the quantum switch and all quantum controlled, coherently controlled situations. Of course, the question is, what exactly is the relation to the quantum gravity theories? And can this help us to do something on the level of the Planck scale? Also, what I just mentioned, but I didn't go into details, and I'm happy to tell you about that later, that there are also processes that displace a strong relation of causality, violate causal inequalities, and this is exactly the Lugano process, but also some of other processes mostly investigated in the group in Lugano, but still we don't know how we can realize them in nature, or of course, if you assume that the causal loops are something which is a realization, then of course, this is a possible way to realize this. But with important footnote that although we have violation of causal inequalities, we don't have any inconsistencies in terms of the grandfather paradoxes. And with this, I would like to thank you for your attention.
Okay, well, thank you very much, Jaroslaw. That was an extremely interesting talk. Let's see, there was one question that showed up in the chat, which I'll go ahead and repeat. So one person asked about the, when you had the counter, counting the number of times that something went through one of the gates, the question was, why doesn't the counter destroy the state?
Mm-hmm. Yeah, I was very fast about that. Yeah, that's true. So let's go back. Okay, so here is the situation. So how we will describe this? Let's say we have a superposition of two paths. And so if we have a particle going this path, the gray path, it will come to this, and the counter will go from 0 to 1. And it will go then further to U0, and the counter will go from 0 to 1. Okay, if we go the other way around, the counter will go from 0 to 1, because this is a different amplitude, has nothing to do with the other amplitude, and then we'll go from 0 to 1 in the U1. So in both cases, no matter which order I have, the two counters will be 1, 1. Therefore, they factorize out of the superposition, can be traced out, and we don't destroy the coherence. Mm-hmm. If this would not be the case, if we have a difference in the two amplitudes, then it will be entangled with the counter, and this will destroy.
Mm-hmm. Okay, thank you. Let's see. Do any other questions? I mean, what you can do is, if you have a question, you can just unmute yourself and go ahead and ask, and hopefully things. Yes, Jarek has a question. Yes.
So I will use the occasion. Caslav, so is there any chance to simulate this gravitational quantum switch in analog models of gravity, for example, by acoustic waves in fluids? There are a series of these analog models exhibiting, for example, something like a black hole analogs. So is there a chance to simulate?
That's a good question. I didn't think about that. I mean, here is really the element that here is relevant is a time dilation, gravitational time dilation. I don't know to what extent this can be simulated. I mean, of course, one can simulate this in different ways. One can have, for example, maybe not the universal clock. The strength of the gravity is that no matter how we have a clock, we introduce the time dilation. But maybe one can have now, going beyond these customary simulations, some clocks that are sensitive electromagnetic clocks that are where I have an electromagnetic field around that will slow down the clock or not slow down, depending on which path the particle takes. But maybe I use this opportunity to say something about these experiments. I mean, these experiments, in my view, oh, sorry, it was later on. These experiments, in my view, are not simulation. In my view, they are really implementations. I don't know why there is no picture now. It's very, that's very good. Oh, that's beautiful. I never know that there are these things. The picture has disappeared. Okay, so there are these optical implementation of the switch. They are not, of course, gravitational switch, but they are the switch in a sense, in my view, in such that they implement superposition of causal order. They can be used in all advantages in quantum computation. By all practical means, they are the switch. Now, there was a huge discussion about something, and this is about locality of the event. Okay, and in the optical switch, it's really bad that I don't have now the picture, but in the optical switch is basically unitary transformation applied, so to say, in one amplitude at one time. For example, L is coming before Bob, is early in time. On the other amplitude, when it comes after Bob, it's at a later time. But, and then people would say, well, this is not a switch because it uses 2 times and so on. But the fact is that it's not, because of the counter argument. We apply this operation once. What is indefinite is when we apply this. It's not that we apply it twice. And so I would say the optical switch is also implementation of the switch where the event or the operation is delocalized in time. And there is a beautiful paper by Ognjen Oreshkov who develops the whole theory of delocalized systems in time. And so it's not that we apply this operation twice, it's one operation delocalized in time. And this is a very different thing than applying twice. Otherwise, all the scaling or the advantage in computation will not be the case. In the gravitational switch, however, and then I'm concluding, locally is always the same event. Locally, by local clock, Alice and Bob, they don't know whether they are before or after the other one. That's nice. Think about the gravitational switch, because locally they can identify this one operation with one time of their local time. And so in a sense, it would be nice to somehow simulate that, that property, but I want to distinguish between something which I feel like is a implementation of the switch, but then there are subtleties there that is related to the gravity, which might be worth then to simulate by analog gravity or something like that. Sorry for the length answer.
Oh, very good, very good. Thank you, thank you.
Let's see, any additional questions?
I had a question.
Please. Hi, Doug.
If you can go back to the promise problem slide, I was just trying to figure out why, like, if you had the 2 paths and you just stuck, instead of entangling the 2 paths, you just put unitary 0 and the order of unitary 0 and then unitary 1 on the top path, and on the bottom path, unitary 1 and then unitary 0. That seems like it would accomplish the same result with the same number of counts that you're counting here. So I'm trying to understand why that's different, what you're getting from this.
I don't know whether everybody understood. I think I understood, but you have to correct me. So the idea of is that we have a similar scheme as this Mach-Zehnder interferometer, but you correct me if I'm not. With a slight difference is that we have an upper path, and then we have U0 and then U1. And in the low path, we have U1 and then U0.
Yes.
Am I right?
Yes.
Yes. Okay. So I would say that the difference, but I think that from the number of queries is the same. Oh, sorry. If the number of queries is the same, yeah. But you need somehow to identify that U0 is the same U0 as here. Not that you have to do it. What I want to say is that the switch has this advantage that it identifies your box, and you can really have a person in this box, so to say, and it will be in acting as operation either before or after. In your
just to
scheme,
clarify,
think,
you're saying basically it's the number of copies of each box. So in this scheme, you only need one copy of each box.
You really need one, and you really identify whatever you do at one place, you do at this one place in your scheme, which will be okay. You will need to have somehow to ensure that it's an identical operation in every such copy. Yeah. And here you have one copy.
Okay, thank you.
Okay. Let's see. There's another follow-up question in the chat. I'm not quite sure exactly. Let me just read it. And is it possible that someone could put up a reference on the delocalized systems in time article? Now, I'm not sure exactly which paper that is.
Yeah, this is the paper by.
Okay, you know.
or Eshkov. I can write.
Okay.
I'm writing in.
Okay.
That's his name.
Okay, great. Okay.
It's a single author paper.
Mm-hmm. Mm-hmm. Okay, I think I will have one final question, and then now, when you actually build these things in the laboratory, how does the advantage manifest itself? Because I guess maybe the advantage of indefinite causal order over causal order, because when you build it in the laboratory, there has to be some kind of causal order, right? Is it the fact that the beam splitters are things that you don't really have an equivalent of that in a circuit, or how does it work?
Okay, so there are, I think, two questions. Like,
okay.
One question is, of course, why this is not in disagreement with the notion that we do have a definite causal order in the laboratory. Mm-hmm. And the other one is more of practical issue. So, mm-hmm. So I would say that okay, some of those process matrices are not in disagreement with having kind of a definite causal past and definite causal. Okay, so let me put about the optical thing, because you asked this. Optical is obviously in a well-defined time. There is a time in the laboratory which ticks, and you do sequential things. However, when you think about in terms of the definition of what it means to have a definite causal order, namely whether the operations themselves are in definite causal order or not, they don't need to be. And this is exactly related to the question of delocalized time, delocalized system. The operations could be so delocalized that although you have a Schrödinger time ticking causally, so to say, the operation is delocalized such that first operation is here, the second here, or in superposition the other way around. Of course, this superposition is controlled by some Schrödinger time, but this is not in disagreement with the assumption that the order of operation, because the operation can be delocalized in this time, Schrödinger time, that they may be in indefinite causal order. So I would distinguish between kind of time ordering and operations ordering. But this could be made even more drastic, I think, in quantum gravity situation in which you will not have the well-defined kind of time, or in time, all time loops, closed time loops. And so in the experiment, I mean, it's really a shame that I cannot show this, but
yeah, I don't know why it's not cooperating.
It's not cooperating, but I don't know. Okay, so doesn't matter. You can apply this at different times. Of course, because it is different times, you have a control. For example, not to go. You cannot go twice through the same point, for example, of the crystal. But you can ensure that the point where you go next time, Alice before and Alice after Bob, are very close, or you can make a tomography before that to convince yourself that they are, on the quantum mechanical sense, indistinguishable operations. Then you can have the same operation applied twice in time.
Okay. Okay, well, thank you.
Welcome. It was a pleasure.
Yeah. And I thoroughly enjoyed the talk, learned a lot, and hope to see you in person sometime in the not too distant future, which kind of applies to everybody here. So I think we'll now move on to Jarek Korbicz. Jarek is at the Institute of Theoretical Physics in Warsaw. And I want to thank the Europeans for putting up with this later hour for giving the talks. And but I don't think, as I said, I don't think we're keeping anybody up. Jarek wrote an extremely interesting paper on the spectrum broadcast structures. Essentially, if the world is described by quantum mechanics, if I look out in my dining room here, things are not in weird superpositions or anything like that. And even though there are quite a few cats around, they're not in superpositions. And they'd be complaining if they were. So how does that happen? So how does our classical looking world emerge from quantum mechanical rules? And that is what Jarek is going to tell us about.
Okay, thank you very much, Mark, for the invitation, and of course, thank you very much for having me here, although only in online version. It's my pleasure to talk about the work I have been engaged in for the past about seven years. And indeed, I will talk about one of the aspects of quantum to classical transition where we managed to say something, I guess, new. So let me give a brief overview of the talk. So first of all, I will introduce the problem. I will be talking about objectivity. So how does it come that or is quantum mechanics able to produce some sort of emergent form of objectivity that we are used to in everyday life? Then I will briefly describe the first attempt called quantum Darwinism. And then I will move to what we have been proposing, which actually builds on the quantum Darwinism. It's perhaps the terminology here is a little bit, complicated, but we really sort of provide a different realization of the quantum Darwinism idea, namely the spectrum broadcast structures. I will introduce them and say a bit about the features, why they work like they work. Then I will go briefly through spectrum broadcast structures in known models of open quantum systems to somehow advertise them to you that it's not just a purely theoretical constructure that exists only on paper or simulated in labs. Then I will come back maybe to more general questions and will show one mathematical theorem how to approach SBS states, or actually a mathematical foundation of how to look for them in practical applications, and briefly discuss the typicality or genericity in quantum measurements. And I will conclude with a set of remarks. So let me begin with the problem. The problem is the following: that in quantum mechanics, as we all know, generally observation disturbs the state of the observed system, unless, of course, the state is prepared as an eigenstate of the observable. Yet in classical world, we do not seem to see that. So, for example, if there is an object on the table, we look at it. Whoever looks at it sees that the object is there and it's not moving. Okay, so the question is how come? Well, Noble is obliged. So if quantum theory is supposed to be our most fundamental understanding of nature, then it should provide some sort of mechanism that would explain or that would show how this type of robust objective features, how they emerge from quantum mechanicals, which perhaps a bit abusing of the language, one can call subjective, in the sense that since every measurement or every observation disturbs a state, so if one observer measures, then the next one comes to measure, then she or he will actually have the state in a different, will have a system in a different state, and thus the measurements will not, or the observations will not have a chance to agree, just because the initial state for the measurement is different for both observers. Okay, so this is the basic idea, and this is of course a problem in a big sack of notorious problems called quantum to classical transition. So how to recover or explain classical world starting from quantum mechanics, assuming that quantum mechanics is the basic description of nature. The problem was maybe a historical remark. The problem, up to my best knowledge, the problem was stated pretty or noticed and stated pretty late in the history of quantum mechanics by Wojtek Żurek and his collaborators, including Jess Riedel, who I hope is there somewhere, Michael Zwolak, Robin Blume-Kohut, and the rest of the group. So it has been noticed pretty lately, about, if I'm not mistaken, about roughly 20 years ago. Okay, so let me maybe give a brief overview of what are different meanings of objectivity. So what we feel somehow intuitively is some sort of qualities or states which are independent of individuals' observation or views, feelings, or interpretations. There is a very actually nice quote which I stole from Wikipedia, and objectivity in science, that scientists, in attempting to uncover truth about natural world, must aspire to eliminate personal biases, a priori commitments, and so on and so forth. I find it quite interesting. Well, we have a sort of objectivity in geometry. Which is the frame invariance. In modern geometry, we view objects as like a vector being a given vector, and we can view this vector from different frames. It's not a change of vector. And then there is a very interesting definition which was given by Wojtek Żurek in his quite well-known paper on quantum Darwinism from 2009, namely that a state of a system exists objectively if many observers can find it out independently without perturbing it. Okay, it looks like an innocent, quite innocent definition, but as I will show you, it has some quite nice consequences. It's quite, of course, compared to all the philosophical problems that humanity has been struggling with, of objective versus subjective. This looks very simple, but the power of this definition is that it has a certain certain operational feeling. So, for example, it becomes now clear what is to be objective. So, what we are seeking to get objective, and this is a state of a system. Okay, so from now on, what I've been talking about when I mention objectivity or objectivization process, I mention state of a system of interest. And well, summarizing maybe these definitions of objectivity, the intuitive feeling would be that something is objective if many agree on it and do not disturb it. Okay, so there are two components: agreement, mutual agreement, and non-disturbance. Okay, and I will build up on that. So yeah, so the question is how that can happen. That despite the fact that observations alter the state of the observed system, how can this happen, or if this can happen, that will still have an objective state coming from quantum mechanics. So the first attempt, as I mentioned, was in the works of a group led by Wojtek Żurek. So Jess Riedel, let me mention again, Jess Riedel, Michael Zwolak, Robin Blumer-Kohut, and the rest of the group. And well, the main idea behind this attempt is that objectivity is in a sense equivalent to information redundancy and non-disturbance. Why information redundancy? Well, when we are to satisfy the definition of objectivity so that many observers can find the information about the state of the system, well, then this information should exist there somewhere in many copies physically. Okay, so it should be somehow redundantly proliferated in some sort of a medium. And of course, the retrieval of this information should be non-disturbing, both to the system that we are trying to learn about, but also to the fellow observers. So we have somehow the mental image behind the quantum Darwinism, and actually the SBS, as I said, the root is the same, is that the information is deposited somewhere in some sort of a physical system in many copies, and can be read out by observers in such a way that there is no disturbance neither to the system nor among them. Okay, and it will all become a bit clearer in a moment. Well, so if I mentioned that there should be some sort of a physical medium that stores this information, and the most suitable framework is that of open quantum systems. If you think for a moment, if you reflect for a moment of how we humans, how do we perform the observation of a world around us, then you will find out that the vast majority, if not all the observations, are done indirectly. For example, the best example is seeing. Yeah, you see me just because there is a flux of photons which reflects over my face, and then is being catched by the solid angle of a laptop camera. Hearing the vibrations of the air, transmit the information in space from point to point, and so on and so forth. So this is to say that indirect observations is something that we are experiencing all the time, and moreover, the environment can be a source of a valuable information about the system that we are interested in. Again, photonic environment carries the information about me, for example, and air transmit the sound waves which are reaching the microphone so that you can hear my words. this is a sort of a paradigm shift in the usual approach from open quantum systems, where environment is treated as a source of noise and dissipation, and is just being traced over, so getting rid over as quickly as possible. While Wojtek Żurek and the collaborators, they reflected back on that and say, hey, wait. But in many cases, it is via the environment that actually the observations are being made. Okay, so to be more precise, this environment, you just to have some mental image, you can think of the usual environments that appear in open quantum systems. So, for example, field modes or mechanical oscillators, some sort of a crystallic grid, or spins if this is in low temperature, and so on and so forth. And now some of the environments, so the following the basic idea, if we accept the indirect character of observations, then and that the environment indeed stores, have a potentiality to store valuable information about the system, then we come to a conclusion that we cannot actually get rid of this environment, because getting rid of it, we get rid of potentially interesting information about the system. So at least part of the environment has part of the environment is monitored. In the setup, a part of the environment is being under the observation, so it cannot be traced out. And this seemingly little step, it actually causes quite a big change, especially on the practical level, since unlike in the usual studies of open systems, we are now interested not only in the state of the central system. So that's on this little picture, this is the central system, not only the state of the central system alone, but we leave some part of the environment under the observation. Okay, hoping that in this part of the environment we will find those informational imprints about the central system. Okay, so this is the basic idea. I will call it a partially traced state, because I will not trace completely the environment. I will just trace a part of it which is unobserved. I think this is easy to understand. It's difficult to imagine in realistic situations that we are able to control all of the environment. For example, now by seeing me, the laptop camera is catching only part of the photons, both in solid angle and in spectrum, that is being reflected from my head, while the rest escapes observation, and in this sense it can be neglected and traced out. But a part not, because it actually carries an valuable information. Okay. For those of you who are familiar with decoherence processes, this is obviously a generalization of a decoherence setup. Yeah, in the usual decoherence setup, the whole of the environment is traced over, while here we admit that in some situations the environment is observed, or is sometimes the only medium that contains information valuable for us, like photonic. So we are not completely getting rid of it, and we leave a part of it under observation. To be more specific, an observed environment is some fraction of the total amount of modes. Maybe I'll come back to this picture, so you can imagine that each little ball here represent a subsystem of the environment. So environment, of course, is a complex quantum system itself. And if we observe just a fraction of it, the question is how to recognize that this redundant information in printing has taken place. So how do we recognize, if we accept this idea that this redundant information plus non-disturbant extraction are equivalent to this operational notion of objectivity that I have given? So the question is now how to check for it. Okay, and the first condition that has been proposed was exactly by Wojtek Żurek and his group and the collaborators in the form of information theoretical equality, namely by looking at the quantum mutual information between the central system and the observed fraction. F comes from fraction, and the observed fraction of the environment. The condition was that as we grow the amount of the environment which we have under our control, under our observation, there should be some sort of a saturation process that, while increasing the amount of environmental subsystems, the mutual information stops growing and it stabilizes at the von Neumann entropy of the central state. So this is the condition which was and still is very popular to check for objective for this operational notion of objectivity. Of course, this cannot stay like that forever, because if we in some imaginary utopian world can control all of the environment, then of course this quantum mutual information will have much more than just the von Neumann entropy of the central state, because of all the zoology of quantum correlations, for example, forms of multipartite entanglement that can come into place as we extend the environment up to all of it. Now, this condition works okay in classical information theory, as one can check. If we have some critical size of the environment past which there is no growth of the quantum mutual information, then this piece of environment sort of contains already the maximum information about the central system that we can extract. Okay, this is so in classical information theory, and of course in classical information theory we don't have a problem of measurement, so we don't have a problem of disturbance. Okay, not so of course in quantum mechanics. In quantum mechanics, like basically how does quantum information theory look like? You have some concepts from inspired or simply just translated over from classical information, and you have to add measurement process. You have to add measurement process at least in that part of quantum information theory which deals with classical output somewhere at the end. Okay, and this measurement process is of course something which has all the chances to introduce all the deviations from classical information theory. And so happens here. It's quite subtle. It was first noticed by Le and Olaya Castro from Oxford, if I remember correctly, in the PRL in 2019, that actually this condition can still allow for discord. So it can still allow for a form of quantum correlations which by definition are non-local. So there is some part of information which is non-locally extractable. That's exactly a definition of a state which possesses discord. Whether this is a problem or not, it's debatable. For us, it was a problem. So how we envisioned how this objectivization process should happen is that at the end we have a state which does not possess any of these non-local or non-locally extractable quantum features. Okay, and so all of that was born the program of spectrum broadcast structures, and we have chosen a different path than the Jurek group. Namely, instead of sort of guessing, probably motivated, one would have to ask Wojtek Żurek and the people from the group if that was a motivation. But instead of trying to somehow guess or adapt classical quantum informational ideas, let's look at the basic definition of what objectivity is and try to make it precise. Just try to step by step try to translate it into a mathematical form. So let me state the definition again. Namely, a state of a system exists objectively if many observers can find it out independently without perturbing. Okay, so what we did, we went literally word by word, trying to interpret or translate words into the language of quantum theory. And here, as you can see, there is one important point which touches actually, which was quite interesting and surprising, which touches the very basic of quantum mechanics. Namely, there is this word perturbing. So we touch the notion of perturbation in quantum mechanics, and immediately this brings us to the celebrated Einstein, Podolsky, Rosen, and Bohr debate from 1935, where gentlemen were discussing of whether quantum mechanics is complete or not. Of course, was the big question, but it boiled down on more technical level to a definition of what is a perturbation in quantum mechanics. And while the EPR team formulated something which can be probably understood as a non-signaling principle, which is given in quantum mechanics for free, then Bohr replied that it's too narrow, that the broader sense of disturbance should be applied. This was not that long time ago, in 2013, very nicely translated by Howard Wiesmann into a modern language of quantum theory, which we use right now. And it can be summarized that Bohr non-disturbance boils down to an existence of a non-devolution measurement, which leaves the whole of this partially traced state, so a trace of a state of a central system plus this environment which we are observing, unchanged. Unlike the notion of EPR, which well, modulo various interpretations, which can be summarized as just the state of the system being non-disturbed, which of course is always in quantum mechanics is always guaranteed if we don't measure the system by the non-signaling principle. So as you see, it's very interesting point, because trying to get a better understanding of a classical limit of quantum mechanics, we are actually using the notions which were put forward there to save quantum mechanics. Okay, so it's some sort of a quite peculiar twist. Bohr was using this notion to show what is quantum roughly speaking, and we are now using it back to show what is classical. And then there is a second assumption, which is fairly technical, and one can actually get rid of it, that the only correlation between the environments is the common information about the system. It's a technical assumption. I will show you later why we used it. Then other smaller things is, for example, find out, the word find out, we interpret it as observers performing von Neumann measurements on the parts of the environment they observe independently, so that these von Neumann measurements are uncorrelated, and so on and so forth. So at the end of this process, quite surprisingly, we were able to put the definition, so put words into quantum states. Okay, we were able to figure out a unique state structure which is compatible with the objectivity definition which I have just presented. As I mentioned, the pivotal thing here was this Bohr non-disturbance interpreted as the existence of non-demolition measurement. There were some technical things on the way as well, like, for example, the states into which the central system is projected are states and not projectors, but these are some technicalities. The most important thing is that following a proper understanding of the definition, following a proper translation of the definition into the language of quantum mechanics, one can get a concrete state structure. We found it sort of like fascinating, and it's probably the most important thing of the whole approach, which makes it sensible. Yeah, so we have a path from a definition to a concrete state structure, and then we can ask question, of course, whether the state structure appears in models or it doesn't appear. Okay, but let me briefly maybe explain what is written here. So as I mentioned earlier, these states I are the states of the central system. So this is the system of interest. These states are usually called pointer states. PIs are the initial pointer probabilities, and if not this tail, that would look like a abstractly written state at the end of a decoherence process, but not here. Here, these states, rho I, are the states of the portions of the environment which are under observation. Okay, very important thing is that to note is that, first of all, they are perfectly correlated to the central system state. So the same classical index I, which enumerates the possible states in which the central system, so the system of interest, can be, the same indexes enumerate the possible states of the parts of the observed environment. And moreover, there is a strong condition that the states with different indices have orthonormal supports. So which means that every eigenvector of this state is orthogonal to every eigenvector of a state with a differing index. This in turn means that these states are perfectly one-shot distinguishable. Okay, and of course the distinguishing, so we can design a measurement which is probability 1, which will tell us which state we are dealing with. And of course this measurement is nothing else as a measurement constructed from projectors on the orthogonal supports of this state. Okay, so now all this talking that I have been doing, now it starts to take a concrete shape. First of all, what is the information, the information that we want to be redundantly encoded? Well, this is the index which identifies in which state the central system is. You can see it proliferated or redundantly stored, because there is absolutely no constraint on how many copies of the environment can they be. Okay, and each of these copy, the state of each of these copy is enumerated by the same index, and moreover, it is easy to convince oneself that when a measurement is performed, irrespectively where it is performed, either on this part of the environment, on this, on all of them, if the measurement is right, so if we ask a right question, meaning if we use the projectors, technically speaking, projectors on the supports of these states, then there will be a complete and perfect agreement between the observers. So they will all observe, they will all agree that they observe the same index I. Okay, so we have the first condition of objectivity fulfilled, that many agree, yeah, many observers measuring this state, due to this property and due to the fact that all the states are enumerated with the same index, will agree on will see the same result. And moreover, again, using it's a simple exercise to look at this state structure and convince oneself that on average the total state, so this whole state of the system and the observed fraction of the environment will stay undisturbed on average. Yeah, we cannot demand too much, so the measurement being non-demolition is in a sense that after the measurement we forget the results. So we want non-disturbance on average, because non-disturbance in each shot, that would be just simply too much. Yeah? That would just basically bring us to the only possibility of being eigenstate of the measure. Okay, so we have here both of the requirements fulfilled, the agreement and the non-disturbance, again understood in the sense of non-disturbance on average. So when we performed many measurement and then average over the result, the average state will be identical to the initial state. Okay. So in this sense, the information about the state, so this index I, becomes observer independent. Okay, and of course, if we should know which question we ask. So if I'm interested in position, for example, I should measure positions. So knowing this classical index I, we will know in which state the central system is. So in this sense, this state will become objective. Okay. It is also clear that this sort of information proliferation, so like some classical parameter being copied in many copies, is the only way to go if we are looking for ideal copies of information. Somewhere deeply there is a quantum non-cloning theorem, okay, which prevents from copying more. Okay. Why is it called spectrum broadcasting? Well, because if you look at the state, then if you forget about this trace for a moment, then these PIs are the spectrum of the state of the system alone. Okay, so these probabilities are, technically speaking, the spectrum of the reduced state, and due to this property, this will be also a block spectrum on each portion of the environment. So this spectrum is being broadcasted. Okay, I should probably hurry up as I have only 20 minutes. So this condition here, there is something I have not changed. I have to apologize for that. So first of all, this condition is stronger than the quantum Darwinism condition, so the one using quantum mutual information, in the sense that a spectrum broadcast structure implies this condition. It's also a very easy, it's very easy exercise. Of course, when I'm showing this structure, this is some sort of an ideal structure. Okay, in practical encounters, in practical realizations, what we can hope is an approach to this structure, but not ideally it. But ideal state leads to the quantum Darwinism condition, so it's a stronger condition. In the implication in the other direction is known. I'm very sorry, I have overlooked this point here. And implication in the other direction does not hold, which means that one has to assume quite significantly more apart from this condition in order to land at spectrum broadcast structure. This was proven. I apologize for this little chaos, but let me quote the relevant paper. This was proven in this paper by Le and Olaya Castro, PRL from 2019, leading to something which they called strong quantum Darwinism. Basically, the idea is that in order to get a spectrum broadcast structure, one has to ensure that all the discord is cut from this condition, and it's quite technical. This proof is really quite technical. It's not an easy piece of cake. Okay, we are very happy because this notion, sort of philosophical notion of objectivity, we encoded it in a quantum structure. Okay, it was quite an interesting and exciting point. Now the question is, of course, all right, great, we have this notion, but does it appear? Yeah, because as you see, we had quite high ambitions. Yeah, we did not want to derive just some sort of an abstract state, but somewhere at the end, we try to probe the question whether the fact that we observe classical world as we do, so we observe it, we experience it as being objective, whether it is being down to spectrum broadcast structures being notoriously produced in the macroscopic situations or not. Yeah, but this is of course a big question. To approach it in small steps, we first started looking at models. I will, and this is the hard part. Okay, all this talking that I have been doing, it's pretty easy to talk, but it's much more complicated to calculate. First of all, because majority, again, if not all, the standard methods of dealing with quantum open systems are of no use here. Just because we are interested in the information in the environment, we cannot trace it out. And all the methods of open systems, they are designed for this step, which is done very early in the development, that you trace out the environment. So the information in the environment is completely neglected. Here, if we work in some approximation, this is to the opposite, so-called recoilless limit. So where not the environment is inert, but the central system is inert, so it does not feel the kickback of the environment apart from decoherence. On a practical level, if we are able to come close to the spectrum broadcast structure, I will explain it later why it makes sense. But here, to give you some intuitive feeling, like, okay, we have the structures. I have done a lot of talking on the motivation and possible foundational meaning, but how to work with them. Okay, so basically, the only thing that we can do is that when we are able to bring a state of the system and the portion of the environment in a form which looks already almost like SBS, but I don't know if these states are distinguishable or not, plus some sort of a coherent part. Okay, then the two natural steps is, first of all, get rid of the coherent part, and this is the standard decoherence process. Okay, this is the standard textbook decoherence process, which in many cases is very well understood. But as you see in this approach, as this is a generalization of decoherence process, this is not enough because we still have to check whether these states are one-shot distinguishable. And for that, we used a state fidelity function, which looks awful. It looks terrible, but actually one can really work with it. It was quite a surprise that with such terrible looking function, one can still work. It does well. It has one nice feature, namely it factorizes with respect to the tensor product, which at some point is important. So well, let me see. Let me check the time. I have about 14 minutes. So I will rush through the models that we have studied so far. The first one was one of the historical emblematic models of decoherence, namely the illuminated sphere model by Jess and Zech from 1985, where we have a small dielectric sphere which is illuminated by a stream, by a flux of particles. We can think of them as photons, and the sphere is initially in the superposition of two spatial states, and it has been proven from this year on that under suitable conditions the sphere will decohere, so the superposition will be destroyed and will turn into a convex combination of a sphere being here or there. The model has been traversed for the past years in many times in all the possible directions, but it wasn't noticed that actually what happens here is if we group the incoming particles in certain groups, we call them macro fractions. This is a technical trick to increase the chance for this function to come close to zero. On a more foundational level, well, imagine that we are using some detectors to observe environment. Each detectors, they have the sensitivity thresholds. So, for example, detectors need some amount of photons per some amount of time to hit on it to produce a click. Well, we can think of this sort of dividing the observed environment into the coarse graining of the observed environment into bigger blocks, as each block representing the sort of a sensitivity threshold. Okay, when we do it, it turns out that, well, there is decoherence, like it has been known from the times of Jess and Zech, but there is also orthogonalization of big enough fractions of the scattered particles, and this leads to a production of an SBS state. We have proven that in 2014, and actually that was the reason. Maybe you remember I was mentioning the strong independence condition, that the only information between the environments is the common information about the system. Well, technically we needed to have a tensor product here, completely uncorrelated state on the portion of the environment, just because we wanted to reproduce what we have seen in the first model attacked, so in this illuminated sphere, but it's not needed. But I will not go into that. Okay, then we studied also spin-spin systems in the most simple form, namely in the measurement limit. So there is just the interaction term, and well, here's a plot for 30 spins traced out as the unobserved part, and 30 spins left over for observation. The green one is the decoherence factor. The green surface is the decoherence factor, and the colored one is the state fidelity. And you can see that these black regions is where both come close to zero. Lambda and beta are the relevant parameters of the initial state of of the environment. So as well here we confirm a approach to SBS states. We studied also registers, spin. Also, we studied spin boson systems. So the central system is spin, which is coupled now not to spin but to a field environment. The question was there if there is any connection between SBS and Markovianity or non-Markovianity, because in this model one can easily control Markovianity by controlling the form of the spectral density. Well, we did not find any apparent connection between SBS formation or model being Markovian or not. And next, this was the toughest example, quantum and still not fully actually finished, the quantum Brownian motion. We had to perform quite a lot of assumptions. The most important one is the recoilless limit. Because of the self-Hamiltonian of the system, it's very difficult to study this model. But in this limited regime, it was possible to show that there is a sort of a spectrum broadcast structure which is actually changing in time, but changes in time in such a way that it at every moment of time it is still a spectrum broadcast structure. We call it dynamical spectrum broadcast structure. But as I said, this was quite rough, and still quite some work would be needed here. We showed also that in the time dilation decoherence of Pikowski and the co-authors, there is also if we prepare the state of the oscillators which are put in the gravitational field in such a way that it does not commute with the Hamiltonian, that we can also show that this that the state of this system approaches SBS, which objectifies, which encodes the height of the center of the mass here. Okay, so I promise to come back to. I have a few minutes. I promise to come back to more general theorems. So, well, as with any new thing, you first formulate it. You try to find it like whether it exists somewhere. You try to find it in models, and parallel you try to sort of formulate some more or less general statements about it. Well, we have two such general statements, and well, at least two. First of all, the mathematically precise theorem on the approach to SBS state. So it would be good to have a foundation of. I just sort of try to convince you that looking at the usual decoherence factor and the state fidelity will be enough. Well, one can prove it, at least for a very important class of Hamiltonians, which have different names in different fields of quantum mechanics. You can look at them as a generalized measurement Hamiltonian, where this is the observable acting on the central system that is being measured, and the measurement is being done via coupling to the measurement apparatus via observables B. In decoherence theory, it's called pure dephasing Hamiltonian, for example. So the question, of course, once we have this ideal SBS structure, the natural question is how far is it? How far is the actual state from the nearest laying, the nearest SBS state? Well, for this type of measurement Hamiltonians, which I've just shown, we were able to prove a mathematical theorem, mathematical lemma, that the trace distance between the actual state and the nearest, in some sense, SBS state is exactly given by the usual decoherence factor plus the sum of state fidelities. So if both decoherence factor and the sum of state fidelities, where A's are the eigen values of the central observable. So when both decoherence and state fidelities decay, we have state approaching to the SBS form. Okay, so this puts a solid ground on what I've been showing you in models. Why in practical searches, why we look at two functions, decoherence and state fidelity. Well, this is the answer, at least for pure dephasing or measurement Hamiltonians. Then finally, well, we addressed the notorious measurement problem. So since at the end of a measurement, we expect the results to be objective. Yeah, so it's not just enough that the result is there somewhere, but it should be at least that would be a good measurement. The result that is well, like the definition says, stored in many copies and faithful copies, and these copies are available for observation without altering the state of the observed system nor state of the companion observers. So the natural connection was okay. So we have this state structure which encodes objectivity. Why not apply it to the measurement problem? Okay, and define that a good measurement is a measurement where at the end there is a spectrum broadcast structure being formed between the system that we are measuring and the macroscopic apparatus. Now I change the language from environment. I go to what I was calling environment. Now I call macroscopic measurement apparatus. Okay, and the question is, if we accept this link, if we accept this connection, so how are those SBS states generic for measurement Hamiltonian? So in other words, what we have been doing in the labs, or just by the forces of nature, so to say, whether it is in accord with the SBS structures or not. And the answer is that indeed it is. And under certain conditions, so for example, we randomize the measurement Hamiltonian by taking the observables from Gaussian unitary ensembles, randomize the initial state. Technically, we estimate the distance to the nearest SBS state, or average distance for a measurement Hamiltonian. It turned out to be actually quite a complicated process, but basically, if the apparatus is macroscopically coarse-grained, and we wait long enough, meaning that there are some sort of a specific timescales for SBS state production, at the end we come close to the SBS state. Okay, so in this sense, generically, with coarse-grained enough apparatus, a measurement Hamiltonian will produce SBS state. So it will conclude with a good measurement if we wait long enough. Okay, so let me maybe finish with some concluding remarks, if I get one additional minute or 2 additional minutes. So first of all, we have shown that SBS appear also in generalized probabilistic theories. So this is this was a work done with Carlo Maria Scandolo, Roberto Salazar, Paweł Chorodecki 3 years ago. So this is a more universal structure than just quantum. In a well-behaved GPTs, one can show that if one poses a sort of a task, which we call objectivity game, then the only solution of this objectivity game are structures which are SBS analogs in GPTs. Objective motion is one of the questions, open questions. So what I have shown was an objectification process of one property, for example, position or spin up or down. But well, in real world is dynamic, so we observe movements, and these movements are also objective. So the question is now how to recover objective movement. Okay, there are some ideas. They are still not worked on, but it's a quite a natural next step. So next question is, given that all that I have said, there is this strong feeling that objectivity is in a sense, it's in a sense an illusion, that it's a property. If we agree that SBS structures are responsible for what we perceive as objective, then that objectivity becomes at least in the sense which I discussed here, it becomes a property of quantum states. So it's in the sense illusional. Well, the next question is, of course, are SBS the spectrum broadcast structures, are they really responsible for perception of objectivity in the macroscopic level? Yes, the next question is, so if realism is a abstraction of the observer in variance of SBS, so that's sort of a philosophical rather question. So when we all see and agree on something, is there some sort of a psychological mechanism which makes us believe that this something exists apart from our observation? But this is more maybe philosophical. A very interesting question posed by Kazimierz Żążewski. So is objectivity a large-scale effect on it? Because as you have seen, maybe there was somewhere in the background that in all the models the environment was big. Then I was also introducing this coarse graining of the environment into bigger chunks. Then what I have not shown, but in practical calculation, one has to go to some sort of thermodynamic limit somewhere at some point. So this all becomes macroscopic. Yeah? And only on that macroscopic coarse-grained level, we have a build-up or approach to SBS. So the question is, so is it only a large-scale effect that maybe on microscopic level we cannot speak of objectivity of any properties? Yeah, the last is maybe also some sort of a wild speculation. So sort of make a connection between geometric and relativistic frame invariance, which is also in relativity frame invariance is observer invariance. So whether there is some connection to observer invariance in the sense of SBS. Well, there is a long list of collaborators whom I wanted to thank and whom I wanted to mention from various parts of Europe. Well, and that will be the end. Thank you very much, and I apologize that I have taken 5 minutes too long.
Well, actually, I think you started a little bit late. So
okay. That makes me feel better. So
okay, so I think you're on time. Okay, well, thank you very much. That was very interesting. I mean, I find the whole subject of emergence of say a classical world from quantum mechanics extremely interesting. Do we have any questions from anyone? You either use the raise your hand thing or just unmute yourself and ask. Okay. Because okay, let me go ahead and ask then. One of the things that sort of in the older writings on measurement problem and things like that is a role of amplification. some kind of an amplifier that takes the microscopic signal and turns it into macroscopic. Does that fit into the spectrum broadcast structure?
Of course.
It does. Okay.
Of course,
Mhm.
it's a crucial. It's actually a crucial point here that this amount of degrees of freedom here, this BKs, that this is a large amount of systems.
Mhm.
In this sense, this is amplification. If you look at the more traditional description of measurement, it has two phases. So there is a pre-measurement where a gentle probe is being coupled, so being entangled to the system. And then there is a second phase of the measurement where this probe is being correlated with some sort of a macroscopic system with a huge amount of degrees of freedom, not to make the measurement process reversible.
Mhm.
Okay, so this huge amount of degrees of freedom is definitely here, and this is what technically makes the state approach to SBS.
Mhm. Okay.
So it is a crucial thing here. If you look technically at how the parameters which control approach to SBS behave, then, for example, decoherence, the average decoherence factor, is exponentially damped by the number of neglected systems.
Mhm. Mhm.
While the state fidelity, the same, it's also being exponentially damped by the amount of degrees of freedom which I group in a fraction and say, okay, my measuring apparatus is measuring this fraction.
Mhm. Mhm.
So this macroscopicity here is absolutely crucial.
Okay. Mhm. Okay. Anyone else like to ask a question?
Yeah, this
Yeah.
is Jess Riedel. Jarek,
Sure.
Hey, Jess.
Stepped away from the computer for 5 minutes. I'm very sorry if you already answered this question during that 5-minute gap. But you mentioned how this spectrum broadcast structure, one of the assumptions or the kind of properties you're imposing is that the different parts of the environment are not entangled with each other. That they are sort of fully conditional on this state of the system. Yep. Or they're completely determined, and is that right?
Yes. We assume that exactly. We assume that we called it a strong independence.
That's right.
Yeah. That's right. So, pardon. What was it? Your question?
Okay.
If we assume it? No?
Well, my question is basically, to me, that seems too strong. That in real life, in fact, the environments are going to be all sorts of entangled with each other, and so any sort of definition, even if we're ignoring kind of issues of approximately and epsilons, that any definition of objectivity is going to need to allow for some entanglement between different parts of the environment.
Absolutely, Jess.
And
absolutely.
I was and so I actually have like mutual information and kind of the traditional Zurich paradigm of discussing objectivity is not actually my favorite way of stating it, of talking about objectivity, but it does have the very nice property that you can just say as long as you have this mutual information between the system and then the different fragments of the environment, it's okay if the parts of the environment are entangled with each other. And so it has that nice general property to it. And I was just wondering why the strong independence, why you impose it.
Okay. Let me. Yeah.
Why not relax it? Yeah.
Yeah. Let me. So, first of all, there is a version of a complete SBS argument which is free of strong independence. It's on the archives. I can give you a reference to a paper which I prepared last year, where I prove all the SBS theorem without strong independence at all. It makes just proof more complicated, maybe more lengthy. But as I mentioned, the why we assumed strong independence was purely aesthetical reasons. It was purely aesthetical reasons, just because when we started to study the concrete models, we were seeing structures which were totally uncorrelated on the environment side. Okay, and we wanted to impose it somehow by hand. I agree artificially on the structure which was emerging from the Bohr non-disturbance. So I absolutely agree that this strong independence is not needed here. We knew it from the very beginning, but we left it just because we wanted to reproduce what is in the majority of open system models. One has to actually work a little bit in order to have here entanglement, but still SBS. And again, the first ones to publish this remark and go beyond it were Tao Le and Alexandra Olaya Castro. In 2019, they noticed that this strong independence is of course not needed there. Yeah, so I totally agree. The strong independence is there put artificially, and it's not needed. I can prove SBS theorem without it, where the SBS structure is a bit more elaborate, because then here is the state which has potentially some correlations, but still has some distinguishability properties. It's just a little bit more awkward.
Got it. Thank you very much.
Okay.
Thanks, Jess.
Okay. Are there additional questions? Okay. Well, I guess in that case, thank you again, Jarek. That was, again, extremely interesting. And I am very interesting introduction to the spectrum broadcast structures. And so we will now break for lunch, and we'll be back at 1:30 with Iman Marvian. Hope to see most of you back here at 1:30. Okay, so we'll take a break for now. And again, thank you to both the audience and the speakers. I think we had an extremely interesting morning.
So first wanted to really thank Mark for putting on this great workshop. I thought the talks so far have been very lucid, so it's been a pleasure. A couple quick things. So my name's Jess Riedel. I'm at NTT Research, which is a still fairly new, I think less than 2 years old, research lab in Sunnyvale, California, in Silicon Valley, that concentrates on quantum computing and some related questions in quantum information. And I'm on the foundational side there. And they have a really impressive commitment, both to kind of unfettered foundational work and also to mentoring students. And so if anybody who's watching this, students who are interested, please definitely contact me. You know, it requires a little bit of footwork, but it's even possible to do a PhD there. That's how actually I did my PhD under Wojciech Zirk at Los Alamos National Lab while I was a grad student at Santa Barbara. And then the other thing I wanted to say about this talk is I really want to encourage everybody to interrupt me with questions as soon as they come. Don't feel like you have to wait until I come to the end of a sentence or a paragraph or something like that. Just feel free to pop in. The more this becomes a discussion, the better as far as I am concerned. Great. So as advertised in big bold letters, I'm going to talk about wave function branches. Let's see if I can. There we go. So the contents of this talk have contributions, especially from Dan Renard, who actually just defended his thesis, I think yesterday, or maybe the day before yesterday. He's going to be a postdoc at MIT. And then Marcus, who is at Google X. And then Kurt, who's at the University of Birmingham. But also, there's a lot of kind of ideas that were germinating here that came out of discussions with Charlie Bennett, Adam Brown, Martin Ganal, Jim Hartle, Wojciech Zurek, and Michael Zvolek. And so you should definitely check out their work. So I'm going to just start out here with a list of claims that I'm going to try to convince you of in this talk. Give me 1 second to just, I need to adjust my, yeah, there we go. So let me get started, and so hopefully I will be able to back up all these claims and get you as excited about this topic as I am. So the first claim is that if you consider it as an entanglement structure in many-body states, then wavefunction branches are a concrete and non-trivial idea, but they currently lack a formal definition. The second claim is that decoherence, quantum Darwinism, and the spectrum broadcast structure programs, some of which that Jarek talked about early in the talk, these are insufficient for defining branches in a foundational sense. They have been useful for talking about them and for getting hints of what they would be like, but they have fundamental deficiencies for completing that mission. The third claim I'm going to make is that locality and redundancy, which I'll say more about, they are plausible first principles from which branches might be defined. And then lastly, I'm going to argue that a definition of branches will have two impacts. One is real-world applications. These could be potentially modest. The ones we are thinking about most carefully are basically the possibility of speeding up numerical simulations of large quantum systems. But this is not, the point is that this is not merely a talk about foundations for its own sake, but it does have real world applications. But then of course, the thing that really drives me, and the thing that I think should drive a lot of people, is that a definition of branches will allow us to ask new foundational questions about large quantum systems and thermalization and some other pretty interesting topics in a way that it was basically just hard to answer or ask those questions before. It's hard to even say what you were talking about because the kind of fundamental structure people are grasping at when they talk about things related to this really is branches. And until you can define them, you're always going to be a little bit confused. Okay, and I just want to emphasize that I really think this is a unusual topic in its foundational importance, and that there's just low-hanging fruit. I don't think enough folks have thought about this. So I want to encourage people to just take a peek at this stuff, because I really think there's a lot to be done, and I don't think necessarily that the approach we've been going on has to be the best one at all. I think there's a lot of different directions to go. Okay, so now to actually get started, the first thing I want to answer is, okay, what roughly do we mean when we say a branch of the wave function? First, to emphasize, this is not going to be dependent on a particular interpretation of quantum mechanics. It's something that can be formulated as a mathematical phenomenon, albeit one that is not yet precisely characterized. So just to kind of defend myself here, I'm going to say that this is somewhat analogous to a phase transition in matter, so just solids, liquids, that sort of thing. So, the existence of phase transitions, the first time you kind of even realize they're a thing, this is indicated by intuitive macroscopic observations. You don't need to do physics or math to understand that there's something interesting going on when ice melts. And as historically as, people sought to understand phase transitions, they, instantiated them in simple toy models. So they didn't go immediately to a full mathematical theory of phase transitions. They looked at very simple cases and then generalized from there. And in addition, analytical computations and numerical simulations provide lots of data in a sense. So if you're trying to define what is a phase transition in its most abstract sense, you can start with specific cases. You can simulate them on your computer, or you can simulate them on pencil and paper, and you get a lot of data. You get kind of emergent behavior that happens that is a step towards then formulating this abstract definition of what a phase transition is. And that jump from observation, empirical real life observation, and then these sort of analytical and numerical simulations, the jump from there to a abstract, fully general mathematical characterization of what you're talking about is hard. It's really not trivial, and there's a lot of important work and kind of insight to be done. Okay, so let's actually say how do we initially start gesturing at what we mean by a wave function branch? So in a unitary quantum model of a measurement, if you say, forget about interpretation. Let's just say I have some, brute force model of a lab that's got a bunch of atoms in it. In such a model, where I'm not going to collapse it ever, I'm just going to give a complete unitary description of the lab, the orthogonal wave function branches that correspond to macroscopically distinct outcomes, which we just say the outcomes of the measurement, those orthogonal wave function components are the branches. So that's what I mean. And as most of you, I'm sure aware, it's basically, if you have a measuring device in your lab that works, then in this unitary model, it's going to create branches. They are unavoidable. So the idea here, is just you take a Stern-Gerlach experiment, you send your electron through this inhomogeneous magnetic field. It is detected somewhere by some transistors where this very weak signal is amplified up. It causes currents, macroscopic currents to flow, even though it was in principle could be just a single electron that was originally measured. And then those currents are amplified all the way up to macroscopic scales that involves like your computer or whatever your readout of your measurement device says up. And that involves, of course, Avogadro's number of atoms. And if it works when you send the electron in an up state, if the measuring device reliably returns up, and if it also does the same, where if you send the electron in a down state and the measuring device reliably returns down with all of this macroscopic correlations that develop, then necessarily, just by the linearity of quantum mechanics, if you send a superposition in, you are going to get a superposition out. But now it's macroscopic because of the amplifying nature of these measuring devices. And so at the vague level, assuming all the structure, assuming this particular toy model, this is what we mean by branches. They are just the two different outcomes. Of course, as everyone knows, this is unsatisfying for many people. It's anthropocentric. It seems to have something to do with laboratory devices in humans. And so we'd really like to eliminate that aspect of our vague definition, to come up with another better definition of something that is a measurement or is a branch without relying on some sort of preferred idea of this is a lab, this is a person, this is our measurement equipment. And so a kind of pretty straightforward and really ubiquitous in the physical world is the outcomes of chaos. So this definition of what a branch is, I think fewer people will have an idea about. Certainly some folks will. I think many people don't appreciate just how common and overwhelming this is in the world. And it's basically just because, chaotic regions of phase space are a large fraction of the phase space of the world. Chaos is everywhere. And it turns out that this is really all you need, more or less, to get a similar sort of entanglement structure that we're going to try to endeavor to make more precise. and it's going to kind of provide us of this intuitive definition of what a branch is in a non-anthropocentric way. So again, just like before, we're going to just think about unitary quantum model of now in this case a classically chaotic system. Again, we're not thinking about collapse. We're not thinking about interpretation. We're just going to do a unitary model, and then given that model, the macroscopically distinct outcomes are going to be generated. They don't require special initial conditions or anything like that, and they're going to be generated quickly. They're going to be generated on the time scale of the Lyapunov exponents of the system. So here I've got a picture of a double pendulum. You know, when these masses are 1 kilogram or 2 kilograms, some sort of very human scale, the lengths are human scales, and the Lyapunov exponents associated with those devices are also on human scales. So this is not something that can only happen very, very slowly. This is not something that is avoided by talking about macroscopic things. And so the idea here is very analogous to our first vague definition. If I start the system in some kind of quasi-classical state, just means, you know, the various masses in the system have approximately well-defined positions of momentum. They're kind of concentrated in phase space, and so we have an intuitive definition of to say, oh, this quantum state of the system has a kind of an intuitive definition or an intuitive understanding as a classical state, and it follows from just like very straightforward, you know, quantum dynamics that. In general, if you start with one of these quasi-classical configurations, you will not remain a quasi-classical configuration on the time scale of the Lyapunov exponents. Rather, you will evolve, the double pendulum will evolve into a superposition of multiple quasi-classical states. And now, of course, in general, if you have a continuous degrees of freedom, there's actually going to be sort of a continuous a spectrum of different outcomes, and I've just simplified it here just for ease of presentation to just have two, but that simplification is not going to change our main conclusions here, which is, why don't we see these in everyday life? Why don't we have to worry about finding our chair at home in a superposition? It's that these outcomes rapidly and irreversibly decohere. So even if you thought for a short amount of time your system could start being in this superposition of quasi-classical states, in a short amount of time it will decohere due to photons bouncing off of it, which in this case are these little purple wiggles, or the air molecules in the room bouncing off the locations of the masses, or you can have vibrations, little phonon modes in the object, and these will very quickly, as I said, decohere, where again you're going to get this similar entanglement structure, this kind of GHZ-like entanglement structure that existed in the vague definition, the first one I gave in terms of laboratory measurements. And again, this is happens everywhere, is constantly happening, at least insofar as you allow yourself a unitary description of macroscopic chaotic quantum systems. And the advantage of this vague definition is, again, it's less anthropocentric, it isn't specific to lab equipment, but it still has big problems that we would like to circumvent. And the first one, or I guess these are both related, is what are these preferred degrees of freedom that decohere? When I said I'm going to talk about a double pendulum, I sort of said, oh, it's in this quasi-classical state that involves, a test mass being kind of well localized in both position and momentum. But that is a particular degree of freedom that is just one of many, many in the system that is in principle constructed of many atoms. Those atoms are not all in classical states. The electrons inside the atoms will be in singlet states. All sorts of funny quantum stuff can be happening at the microscopic scale. So there's some subset of the degrees of freedom that are doing these classical things that we're using for our vague definition. And so we have to get more precise about that if we want to formulate this mathematically. So what we're going to be driving towards is how do we define this from first principles. So before I go on, I just want to take a second to see if does everybody sort of buy that? Okay, I will assume you are all totally convinced. So now I'm going to talk about why decoherence is the decoherence program is insufficient for this sort of an explanation. So the decoherence program is grounded in a preferred system environment tensor decomposition that kind of comes from nowhere. We just use our intuition about it. And in particular, if you had a simulation of an arbitrary set of atoms on a computer, it would not be so clear what is the system and what is the environment. So the decoherence problem or program shows that if you're given plausible initial states and interactions, then this initially pure isolated system will irreversibly decohere in a preferred basis that intuitively corresponds to branches. And it allows us to generalize it away from the lab. So there's no measuring devices, but this still requires preferred degrees of freedom. So one way to say this as a catchphrase is that decoherence solves the preferred basis problem. It tells us kind of what the branches are in a certain model. Basically, you know, it's not quite the Schmidt decomposition, but it's something like the Schmidt decomposition of the system. It says, in what basis is this system entangled with the environment? But in doing that, it creates the preferred subsystem problem. So if you were negative, you would say it is sort of, you know, hiding the problem or reducing it is an optimistic way to say it. Certainly, I think the decoherence program has been immensely illuminating on understanding how branches form. But there is this remaining rub, which is what are the preferred subsystems? If I just look out into the world and it's, you know, 10 to the 50 atoms, it is not at all clear what the ways to group those are into systems that behave classically. And you certainly can't take a random set of degrees of freedom. Any individual electron will not in general behave classically. Any random summary variable of many electrons will also not behave classically. So there's a lot of work being done in this choice of what the preferred system is, but that is not specified in the decoherence program. So we are left with this idea. What are the subsystems that decohere? So just to make this a little bit more concrete, I'll give you some examples of preferred subsystems and give you a sense of the kind of breadth. It is, of course, much bigger than the points I put on the slide. But so, you know, the classic one maybe is the center of mass coordinate for a macroscopic number of bound particles. So the dust grain that is being decohered by light. A little bit less of a toy model, kind of closer to kind of more sophisticated and difficult to analyze systems are hydrodynamic variables. So these are the local spatial averages of conserved quantities like energy, angular momentum, charge, particle number in systems, especially systems where the hydrodynamic approximation is accurate, which is to say on small volumes of the system locally equilibrate quickly, but the conservation laws mean that in order to transport these conserved quantities large distances, that takes a significantly larger amount of time than the local equilibration time. And so therefore the system is well described as a bunch of volumes, each one which is locally thermalized, conditional on the values of these conserved quantities. And then the question becomes the dynamics, in this case, quasi-classical dynamics of those conserved quantities at different positions. And you can also find preferred subsystems in the source configuration for long-range fields. There's a sense in which any set of charges that have a long-range field like gravity or electromagnetism. They're sort of constantly broadcasting their position just by virtue of the fact that they're tugging on the external environment. And this often acts like a system environment coupling in the way that's relevant for decoherence. And so all of these are sort of intimately connected to locality, which is to say things tend to only communicate with stuff that are near them, or at least are a signal has to propagate from one to the other for them to connect. And also to many-to-one interactions, which I won't say too much more about, but there is a sense in which, as is kind of more fleshed out in the quantum Darwinism and spectrum broadcast structure programs, there is a sense in which a key feature is that the system talks to the parts of the environment more strongly than the parts of the environment talk to each other. However, this is sort of a vague idea. No unified theory of this exists. And just to put a little bit of a finer point on this, we can ask, well, are there alternative ways to decompose the world that are equally good? So you can kind of imagine you have your Hilbert space, you identify a system using some tensor structure, the rest of it is the environment. But then you can say, well, what about this other system? If the blue choice of the system S, if it behaves quasi-classically, does that mean the green system S tilde could also behave quasi-classically? Would there be branches in those two cases? Are these intuitive degrees of freedom we prefer unique? And the reason this is important is because if you're trying to use the decoherence program to define branches by identifying a preferred system, if there's different choices of systems, you could do different branch structures. And this does not seem to be, at least on macroscopic scales, the situation. We seem to have universal agreement, and we would also agree with any aliens we met, sort of what macroscopic events happened and which ones didn't happen. That is to say, we expect that there's some sort of a objective, perhaps not, perhaps only up to some epsilon accuracy, or perhaps other, minor caveats. But we expect there to be basically an objective agreement about what happened, and that there is not a preferred, or rather, there's not a alternative way of decomposing the world into branches that is just as good. But in order to identify what makes the branch decomposition, we think is intuitive and natural, we have to find principles that pick out that branch decomposition from other ones. So these questions have definitely all been asked before, but I think there is no good answer found within the decoherence program. Quantum Darwinism and the related spectrum broadcast structure is better. It is telling us something important, but it does not solve these problems. So both of these, like decoherence, are grounded in a preferred decomposition into macroscopic parts. In order to say that a chunk of the environment has information about the system, the environment has to be big enough such that it can actually have a full bit of information. And in this room, if I just picked an electron, it would generally not have enough information to tell you about any individual system in the room. So it has to be this macroscopic part. And we are still relying on this as yet unexplained choice of what the system is. Sorry. So we haven't gotten away from that problem with quantum Darwinism. However, it did reveal, or at least emphasize maybe, or made more clear and precise in people's minds, an additional special property that these preferred systems have, and when you include looking at the environment and its many parts, is this idea of redundancy, which was something that was not as easy to analyze just from the traditional decoherence program. So, although these special properties have been pointed at, it is still unclear whether the decomposition above, this system, environment, and the macroscopic parts, whether this is unique or there could be many alternative ways that are incompatible with each other of thinking about this particular quantum universe. And we're just left with this question again: is what is the system and what are the parts? Okay, so now I'm going. So hopefully, I've at least established that this question is as yet unanswered, and I'm going to say a little bit more about just should you care about it. I want you to just imagine you had a guarantee that non-trivial mathematical structure that robustly described branches. Somebody gave you a definition out there. Imagine you were guaranteed it was just waiting to be found. I don't understand how people could not want to understand this. It is so foundational, the way we talk about quantum mechanics, the way we think about the world. At the very least, you would have an answer to the question of what is a measurement. You would no longer have to sort of wave your hands. You would no longer have to even talk about there being some sort of anthropocentric answer to this. You could just say, listen, if we had, a conditional on us having this definition of what a branch is, you'll be able to say, oh, a measurement is just when a mechanical device creates branches. Branches are being created all the time out in the real world. Some of the times we engineer these devices to create branches in the basis that we want them to be created in, in the Z basis of this particular electron spin. But it is a natural and precisely defined phenomenon. I think this is a clearly much more satisfying answer than what we have been reduced to for talking about quantum mechanics up till now. So given that foundational importance, I think you should be excited. So I think I've argued so far that we don't have an answer to this question. And on this side, and I certainly have more things to say, I'm arguing that if you knew that an answer existed, you should be excited and want to know. So then I think the only question is there something there to be found? Or is this just an intractable problem? And it's just, yes, it's hard, or yes, we would like to know better, but there's no hope. So I'm going to try to show in the rest of the talk that there is something to be found, and that this should pull you to be thinking about these problems. Okay, so here's one motivating question to maybe draw this into more stark relief. I alluded to it earlier in the talk. Is if you were going to simulate the universe on a computer, how would you identify the preferred systems or the preferred branches? So take some sort of a condensed matter lattice system, or imagine the quantum fields. Just in principle, what would you even say the branches were? And I think what people mostly do in this circumstance is they just fall back on toy models. They say, well, we have these systems we've analyzed of dust grains decohering or very, very simple things. And, the things that happen in the real universe are basically like this. But if you wanted to do this for you just had a description at the microscopic level of the universe on your computer, this would not be sufficient. It would just look like a giant mess. So here's the proposal that I'm going to give. Most of this is going to come from the archive number at the bottom right-hand corner of the screen there. And the proposal is that we start only with the microscopic structure that is associated with spatial locality. So this microscopic structure will not have systems in it. It will just be things, if you really wanted to get foundational, it's like these are the spatial modes of the quantum field. I am not worrying about superpositions of causal structure in this talk, so I am going to help myself to at least a classical space-time background. And so we're going to take our notion of locality to be something that's quite fundamental and that we can kind of put our weight on. And the question is can we get systems to emerge from that? So in order to think through that question, I just want to like go back to the, this original picture of a chaotic system that is generating macroscopically distinct configurations, called quasi-classical configurations, and then is being decohered. And just ignore which subsystems we think are special there. So kind of treat the system and the environment on equal footing. And so just eliminate that picture and just look at the structure of the state. And the key thing is that this branching state retains this GHZ-like entanglement, even if you don't think about which is the system and which is the environment. And so that's the direction I'm going to try to head. And before I get into the details here, I just want to emphasize again that this approach is just an idea. It's the one that I find most promising. But even if I'm completely misguided on this, the problem of defining wavefunction branches remains intensely important. So everything I said in the talk up till now still holds just as strongly, even if you say, oh boy, I don't want to rely on locality. I would prefer to rely on some other fundamental way of identifying branches. But let's dive in now as a way to try to convince you that there's something there to be found and to make precise and analyze. We're gonna dive in to this particular approach. So this is the kind of the part of the talk with the most formalism. So I'm going to go through it slowly. It's really not that much. And I, again, really want to emphasize that people should ask questions if they are at all confused. So the first thing I'm going to define is what I mean by a record. So again, we're starting with we've just broken the world up into small spatial regions. So just think about the kind of traditional many-body lattice. And that's the only structure we're going to assume is that, and then the state of the system. When I define a record, which I'm going to do on the next slide, a record is going to be associated with a certain region of the lattice. So just some subset of the lattice. I'm mostly going to be thinking about it as a contiguous subset, but it doesn't necessarily have to be. It's just some subset of all of the lattice sites. And now if I want you to consider an eigendecomposition of a local observable in terms of local projectors. So you have some region, R, which is red on the slide. Then any Hermitian operator can be expressed in this way as this sum of the eigenvalues and the projection onto those the subspaces associated with those eigenvalues. And we're not even going to be talking about the eigenvalues. The only thing that matters that the eigenvalues need to do is to be distinct. But our definition of record is not going to rely on the value of it. So it's really, instead of thinking about it as records associated with or related to observables, it's going to be sort of records related to these sets of projectors. And that's the thing that we're going to talk about being recorded. The kind of elementary property that we all know from basic quantum mechanics is that when you do this sort of a decomposition, these are complete sets of orthogonal projectors on the local regions, right? So they're orthogonal in the sense that they're Hermitian. You take the dagger of them, and they are unchanged, and they can be expressed as an operator that acts on the Hilbert space of the region, tensored with the identity on the complement of the region. They are complete in the sense that when you sum them up over I, over the index lowercase I, you get the identity. And they are orthogonal in the sense that, if you combine them together, pi times pj, then they annihilate unless I equals j. Okay, so here's what I mean by a record. Given a pure state and two disjoint regions on the lattice, I'm going to say that one local observable records another local observable when their eigenvalues are fully correlated with this state. So I'm always going to be talking about a given lattice and a given state, okay? And so this is the condition for saying that the observable on region 1 records the observable on region 2. As promised, this actually doesn't really matter about the eigenvalues. You could consider two different observables that you got by just changing the eigenvalues while leaving the projectors the same. And you would, even if you change the eigenvalues, as long as they're distinct, then this condition would continue to hold. So it's not something that's sensitive to that. But of course, if you rotated one of the observables, this condition would potentially break down. Okay, so that's one way to define one observable, a local observable, defining or of having a record of a different local observable. I'm going to give you an equivalent definition. I'm going to say that we have a record when the reduced state at one region, the reduced states, I should say, at one region, conditional on different values of the observable in the other region are orthogonal. So this slide has just a little bit more notation on it, unfortunately, but it's a very, very simple idea, which is that if I go to one region, in particular region 1 in this slide, and I project the state onto the subspace associated with a specific eigenvalue of that observable on region 1, then I have a conditional state on region 2. And I can do that for the different eigenvalues on region 1, and I will get different conditional states on region 2. Now, so I'm going to say that the observable on region 1 records the observable on region 2 when these conditional states are all orthogonal for I does not equal to j. And it's very simple to see that this is equivalent to the thing I first said. And the intuition here is that when you have this, it means that an observer, so from outside the system, could in principle infer the value of one of the observables by making a local measurement on another observable that records it. Okay, so now we have this idea of observables on disjoint regions of the lattice recording each other. And the first thing to notice is that this, R1 records R2 is a symmetric and transitive relation on local observables. So that if R1 records R2, then R2 records R1. Likewise, if R1 records R2, R2 records R3, then R1 records R3. And then the thing we're getting at is that these different eigenvalues that are all perfectly correlated with each other, this is going to be the branch, or at least the candidate branch, the kind of thing we're gesturing at in a specific case. So if I have a set of observables, right, because it's a symmetric and transitive relation, I can always say these observables record each other, and that's an unambiguous statement. Given that set of observables, I can unambiguously talk about the branch or the candidate branch. Maybe we have to say more about it, but there is an unambiguous component of the wave function for the whole system that is associated with these matched values of observables on different regions. And in particular, I'm going to require that these candidate branches are simultaneous eigenstates of at least 3 recorded observables. So as I talk more about in the paper, there's this very important jump from 2 to 3 that I'm sure you're all familiar with, which is that if you have a bipartite GHZ state, which is to say a Bell state that's balanced, so if you have up, up plus down, down, this does not select out a preferred decomposition because of this very special situation with 2. And so we're always going to require at least 3 observables because once you go from n equals 2 to n equals 3, you suddenly have a significantly more rigidity. Okay, so now I'm going to introduce a definition. So given that definition of what records mean, I'm going to introduce a definition of branches. So before I was talking about candidate branches, now I'm going to say what I actually mean by honest to goodness branches. This is not a great definition. This is a definition that has several very nice properties, but it also has properties that make it unsuitable for saying, oh, we've solved this problem of defining wave function branches. But I think it gets surprisingly close, and in particular, much closer than kind of what was known before it. One of the deficiencies of this definition is that it's going to rely on a fundamental scale, literally a length scale. And this is not something that you would expect for any sort of universal definition of what we mean by branches in quantum mechanics. But it is going to rely on just one length scale, and then we're going to get a huge amount of structure that naturally emerges from that. So again, we're going to assume we have a lattice. We're going to assume we have a state of the system on the lattice. And for this particular case, we're going to assume we're just given some length scale. And then we're going to define a set of branches with respect to those three starting assumptions. Okay, so we define a redundant set of observables at scale L to be a set of 3 or more local observables that fit in disjoint spheres of diameter L. So, right, they can be any shape, but the point is that they have to be sort of non-overlapping and separated by at least this scale L. They can't be super stringy and extend way out much larger than L. They can't be all packed together very closely, all together smaller than L. But we're just assuming that we have some set. In this case, I've drawn 4 observables that record each other. That is to say, they're classically correlated. They have this GHZ-like structure. Now, I want to emphasize that I'm not saying that they are actually in a GHZ state. They can have all sorts of entanglement. These different regions can be entangled with each other in different ways. They can be entangled with the rest of the lattice. So this is not definitely anything restricted to specifics of GHZ. They just have to obey this bottom line, which is to say, if I project onto the ith, or I guess that's jth eigenvalue in one observable, if I just apply that local projector on that one region, then the global state of the entire lattice collapses down to an eigenstate of the corresponding projectors on these different regions. Okay. Okay, so that was a statement. That was a statement about what I mean by a single redundant set of observables. Now I'm going to consider multiple sets of observables. So you can think about this as just different sort of information that is contained. So maybe the red observables here are the various records of some macroscopic event that happened, like the result of a Stern-Gerlach experiment. And then these blue regions are the result of, excuse me, some other macroscopic event that happened, what the orientation of the double pendulum ended up being, and so on and so forth. So we're thinking now of multiple sets of redundant observables that are going to be interpreted as multiple different questions or different global variables that are macroscopically recorded. So here's the main result is that given a state on the lattice, given that tensor structure that defines the lattice, and then given a length scale, then all sets of redundant observables at the same scale L necessarily commute on the state. So there you can simultaneously measure everything in the system that is recorded on scale L. And again, record means has at least 3 records. Okay, this then lets you define the branches at scale L to just be the simultaneous eigenstates of all of the redundantly recorded observables. Again, you don't have to, in order to make this definition, I'm not specifying, oh, this observable is going to be here in this region, this observable is going to be there in this region. I'm just saying, consider a state on a lattice. Consider all the observables that for this state happen to be redundantly recorded on at least 3 regions separated by this length scale. Then there is a unique decomposition of the global state into simultaneous eigenstates of all of these observables. And so this is basically the claim that at least if we assume that things should be recorded on a certain length scale and not kind of arbitrarily packed together or arbitrarily records that are stringy and stretched over, galactic distances, then there's an objective notion, at least with respect to this length scale, of what the branches are. That all of everything that's been recorded in the sense of quantum Darwinism, that there are simultaneous eigenstates of these things. Okay, so that was the results that motivated that. I think there's something there, that there is a bunch of structure out there to be found. And as I said, there's deficiencies with this definition. And so I would love to see improvements on it. But I think there's definitely stronger results out there waiting to be obtained. Now I'm just going to briefly talk about some of the potential real-world applications of being able to define and find branches. Do we have a question? No, I think not. I guess that was just some background noise. So now I'm going to talk about real-world applications that have to do with efficient simulation. This is pretty speculative in terms of will this be practical anytime soon, and will this basically be substantially better than everything that's existed up to this point. These are unclear. Maybe the results of this are sort of modest in terms of the real world importance. But I think the fact that it is allowing you to do something concretely better gives us additional confidence that this branch structure is important and worth pursuing. I'm going to talk a little bit about tensor networks here. I think it's literally just 2 slides. So if you don't know anything about tensor networks, don't worry about it. Just try to get the gist of what we're talking about. So it's well known that if you're trying to simulate a large quantum system, something like on a lattice, you can't generally fit that state on your computer. The number of numbers you need to represent an arbitrary wave function for n particles is exponential in n. However, states with low amounts of long-range entanglement have an efficient description as a tensor network. It's just a representation of the state that you can manipulate, and it represents a kind of small fraction of Hilbert space, but it's an important fraction of Hilbert space, and it's one that has been used to dramatic success for answering a lot of important questions in condensed matter. However, even when you start with these states that have an efficient tensor network description, or again, just think about it in terms of they don't have much long-range entanglement. Things can be entangled locally quite strongly, but they are not sort of a crazy superposition of very different things going on large scales. The problem is that even if you start in one of these special states, then for essentially the same reasons as I described with the double pendulum, out of equilibrium states are going to be generically generated. That if you have a non-integrable Hamiltonian, that is basically isn't kind of especially fine-tuned, it's going to take one of these simple states and over time generate long-range entanglement, and your simulation will get slower and slower until you can't run it anymore. And this is like an exponential explosion. So it's without additional tricks. If you're just looking at a generic system that you haven't been able to find specific tricks for, there's a pretty hard time horizon on how long you can simulate this for. And our speculative proposal is to decompose the state into branches, each of which has less long-range entanglement. Exactly, it's unclear how much less, but you can definitely get a significant decrease in the amount of long-range entanglement. And then, as I'm going to explain on, I guess, just one more slide that has to do with this numerical simulation stuff, it will in particular, like, you're going to have to throw out information when you do this, but the claim is that, you can't keep all the information because you can't keep the entire wave function on your computer if it's this general, very highly entangled state. But the claim is that you will be able to estimate correlators of local observables by sampling branches. And this is in some sense kind of what the actually experimentally relevant parameters are. And so this slide is just to basically describe that procedure, that if you have this branching algorithm that efficiently finds branches, this will say why that works. This will be very elementary for anybody who just knows Monte Carlo methods in condensed matter. We're only adding a tiny little wrinkle here. So the idea here is that you have some correlator. You want to say, I'm trying to calculate this endpoint function or something of a few local observables in this quantum state. And if I have a branch decomposition, I can, of course, expand this expression in terms of the branches. So I expand the state on the left and the right side. And the key idea is that the branches are going to be, as promised, the branches are simultaneous eigenstates of these local projectors. So I can pick one of the regions and I can say, okay, I know there's a record of this of the observable associated with the ith branch on this local region. And so I can just, I can basically insert that projector on the second line there for free. And if I have a sufficient number of records, then I can always find one that is not overlapping with the local observables that I care about. That allows me to commute it through this expression on the right-hand side there. And then because we know the branches are simultaneous eigenstates of all these projectors, that will in general annihilate the right-hand side unless I is equal to j. And so now we're left with this classical sum. It's a probability distribution. And it's well known that once you have your endpoint function that you're trying to compute in this form, then you actually don't need all of the terms. You only need a sample of them. And in particular, even if you have an exponentially increasing number of branches, and that is what will generally happen, that as a non-integrable system evolves from a low entropy state, it's going to be generating lots and lots of entanglement. Any branch description, it's going to be producing branches very quickly, just as a double pendulum is producing branches at a regular rate. The number of branches is going to be growing exponentially. In order to estimate these local correlators, and again, the local aspect was key here in order for this argument to work, you can just sample from those branches. You don't have to keep all of them. So the idea is that you run your simulation, you identify branches as they form, and then you just pick ones that you go down. And this can then just becomes this kind of classical Monte Carlo simulation. And it's very, very straightforward to show that you can get an accurate measurement with a polynomial number of branches, even though there's an exponential number of branches in the entire system. Okay, so now just a few slides to summarize. So first, I argued for the foundational implication of branches, that it in principle reduces quantum mechanics basically to a classical stochastic theory. It reduces the uncertainty part of quantum mechanics to a classical stochastic theory, where each branch would represent a distinct macroscopic outcome. And again, as you would expect, the probability is given by the norm squared of the branches. And importantly, it means that laboratory measurements, they just become a subset of this natural and mathematically well-defined phenomena if we can define it. So that's the work that remains to be done. And then the practical implications is that if you can identify when collapse has effectively happened, and these branches have formed, then in principle, numerical simulations should be able to treat these what look like very complicated entangled systems. They should be able to efficiently compute these local correlators using classicalist sampling over branches. Again, you would simulate the system, identify branches as they're found, and then prune the branches by just picking randomly from which branch to follow. And this would, you only follow kind of down a very tiny subset of the number of possibilities in this tree of branches. And this has the potential to reduce the exponential explosion in computational resources necessary to simulate many-body systems. Now, if that will be practically useful is very, 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 very unclear at this point. But I do think that it is a hint of the importance of this idea. In particular, if you're familiar with tensor networks or matrix product states, the branches are going to correspond to blocks in the matrix product state representation. Okay, and then lastly, just finishing up here, you can now, if you could have this definition of branches, there are new questions that was basically very difficult to ask before, but now you would be able to ask them and ask them precisely, proof theorems about them. So first, what is the rate at which branches form? Is it given by the Lyapunov exponent, which basically is, you can kind of more formally generalize in terms of this Kolmogorov-Sinai entropy? Would we really have a unique set of branches? Would there be some sort of remaining ambiguity, especially at microscopic scales of kind of what the branches are? How approximate are they? How precise can you make them? And it may also allow you to be more, less confused, we'll say, when you're thinking about quantum gravity systems where locality may break down. You can imagine a situation where, with respect to a classical background metric, there is a unique branch structure. But in a quantum gravity situation, there's perhaps not a unique branch structure. I mean, there's incompatible branch structures. And there is at least a couple of cases where people have claimed that, one thing that is confusing is that when people are thinking kind of traditional quantum mechanics, we make measurements, that's what quantum mechanics tells us. That works when you're not working with quantum gravity. And that when people are thinking about quantum gravity, they kind of are implicitly thinking that they can keep doing this. And that if locality is breaking down means that these branch structures is breaking down or they become ambiguous, then that may clarify some confusing questions. And then another thing you can ask, which is actually one of the things that originally got me interested in this topic, is how long can branching go on for? When you're presented with quantum mechanics, when you initially learn about it, because the measurement postulate is sort of this outside thing that you collapse down to the state that corresponds to the outcome. It keeps evolving. The rest of the state you throw away and you never think about again. That suggests that this can keep going on. But if you give a unitary description of the universe, of course, this actually can't go on forever. Whether or not the Hilbert space of the universe is actually finite dimensional or infinite dimensional actually doesn't matter. The Hilbert space of the universe is effectively finite dimensional because the extreme IR and UV modes are basically inaccessible. Certainly inaccessible, or certainly shouldn't be relevant to maintaining the orthogonality of branches. And the branches have to be orthogonal. If we're going to give a probability interpretation of them, if you want your probabilities to be positive in sum to 1, the branches have to be orthogonal. And if you have this effectively finite Hilbert space dimension, you have a orthogonal number of branches, this branching can't keep going on forever. And so what happens then? Does classicality dissolve? And if so, when? And is this the same time point as thermalization? That's what I expect is that basically the collapse postulate of quantum mechanics stops working, it stops being sensible when the universe reaches heat death. But of course, that is in some sense okay, because there won't be experiments around that are operating at heat death in order to show that it's wrong. So that's the end of the talk. I really appreciate the attention, the citations below, and I'd be super eager to answer any questions people have.
Okay, well, thank you very much. Jess, that was very interesting. Well, let's see. Let me start things off. The scale, the L. Does the size of it actually matter, or is it just the fact that it exists matters?
Yeah. So you need to pick a scale, and nothing else in the problem has a scale. So it doesn't matter which one you pick as long as you stick with it. However, you can have a particular state on a particular lattice that would have distinct incompatible branch structures at different scales. Okay. And you know, basically what's going on is that the counterexamples for this stuff, the counterexamples for having uniqueness of branch structure at all scales, are coming from quantum error correcting codes. And so, you know, if you have this, like, you have things like a short code where you have redundant copy, you know, the whole idea behind a quantum error correcting code is you want to have redundant copies of the information. And the way it has to be stored is you sort of have redundant copies of the X information. You know, you can think about it like a grid. So each column might have you know, on the lattice would have a copy of the X information. Each row on the lattice would have a copy of the Y information. There's in some sense, you know, redundancies of those incompatible variables. And those would then, there's no clear branch structure because there's, you know, there isn't a preferred variable here. There isn't a preferred basis that gets selected out by the shortcode. It's a coherent state. And it's, hopefully it's clear to see that that basically, this fact that all the records are sort of carefully overlapping with each other is totally crucial to making the shortcode work. And it is the thing that is ruled out by having these things separated from each other, kind of contained in L-sized balls. That's the role that the length scale is playing. Okay. Okay. Are there other questions? Okay, well, if I guess if not, we'll go ahead and thank you very much for the talk, and we'll go ahead and end things now. Again, thank you to the audience for showing up, and thank you to the speakers again. And yeah, it's been, to me, an extremely educational and enjoyable conference.